You are currently the only person in this conference.
Good morning, everyone.
Good morning.
Well, how are you this morning?
Coming along, bright and early. I did my chocolate instead of coffee, but yeah, same effect.
Oh, really? Well, yeah, I just got my coffee. It's a latte, so I cannot complain. It's really good.
There you are. I did Lint, so I can't complain either. I was hoping that one of the things I messed up on is I didn't reach out to Marco Elver. He might make it for the last 5 minutes. If he doesn't, then I'll reach out to him afterwards. But
It's all right.
Here we are.
Yeah, I have the special card for the last 5 minutes.
Okay. All right. I suppose I could turn video on here at some point, couldn't I?
Yeah, when you're presenting, if you can turn actually, you can turn it now. We have 5 minutes before the start.
Yeah, it often gets confused, so I figure I better do it now. Okay, it didn't get confused this time, so that's a good thing.
Well,
there, look at that.
Audio is really good. Oh yeah, looks perfect.
Let's see, I could line that up a little bit. There we are. Yeah. I guess we got a few minutes. Oh, I did. I think it's probably too late. Marco did note a typo. It's not a big deal. So it looked like the slides are already being converted. We'll use the old slides. We'll get to the typo. It'll be fine.
So yeah, I made the presenter.
Okay.
It should be all good. I uploaded your slides from 10 minutes ago or so.
Oh,
so
thank you.
Okay,
great.
Yeah.
All
no
right.
worries about typos.
Thank you, Daniel. You're on time.
Yeah, all right.
Perfect.
Sometimes, sometimes it helps to have moderators who are on the ball, and so thank you both. All right, so now I should figure out how to do the screen share thing back from last year. And we've got this, which make full screen settings about, nope. Let's see here, I've got that, which I don't know, it's not showing a pop. Oh, that's audio. I can raise my hand. I can make the presentation full screen. I can hide the presentation. I can go up here and not much happens. You know, this used to be easy. Let's see here, what do we got going on? Set status. All right. Okay, guys, what am I supposed to do to share my presentation? Are you guys going to do that? Do that and get rid of the sidebar, but that isn't helping, or maybe it does. Let's just take a look and see if there's something extra around here. I don't have the. I could make Alexi full screen. I can check my connection status.
Well, while you're looking for the slides, the conference organizers asked us at the beginning to go through the sponsors, and thank you, our diamond sponsor, Facebook. Thank you. And of course, platinum sponsor, IBM. Gold sponsors, ARM and Microsoft. And silver sponsors, AWS, Netflix, and Red Hat. Speaker gift sponsor, Collabora. And t-shirt sponsor, VMware. And of course, for the concern services, we're pleased to have Linux Foundation. And of course, thank you for LPC Planning Committee making this conference happen. Paul, go ahead. You can. I think you have all the controls.
All right. Oh, yes. Look at that. All sorts of new stuff appeared there. Thank you. I was trying to jump the gun was what was happening. Okay, today I'm going to talk about BPF Memory Model. What's happening is we have a lot more concurrency within BPF programs, BPF user space, and the rest of the kernel. So there's a motivation to have some way of organizing this. I'm going to go through the first part of this rather quickly. It's a recap of what I presented last spring, and it's mostly there for completeness. But in any case, this is the agenda we're going through. We're going to be focusing most on item 6 here in this agenda. But memory model, concurrent accesses, hope you know what data races are. We have a Linux kernel memory model that is not the C standard. That makes life interesting. And on the bottom of a lot of slides will be little URLs like on this one, and that's where we have LPN articles and other things that give more detail. Compilers can do all sorts of nasty things to you. Here's a list of them. And the hardware can do nasty things too. It's not always straightforward. And even on x86, we have these issues. So the Linux kernel memory model is what makes sense. BPF interacts very closely with Linux kernel. That's the only real choice. There is some overhead. The added overhead on x86 is less than on the weakly ordered machines. But things like atomic operations, shared memory atomic operations are more expensive than simple loads and stores. The atomics also incur cache misses, so it's not just the memory ordering overhead. All right, the answer to that one is easily no. Here is a partial list of the atomics in the kernel. We should add them as they're needed. In addition, there's a lot of helpers. A lot of the concurrency is handled by the helpers. Those are written in Linux kernel code rather than as BPF programs, and they can take up much of the concurrency load. Not all of it, much of it. Okay, here are some that have already been added and some that might be added. The basic thing is the ones that are most useful, most straightforward, and most needed. Okay, so again, an appropriate subset of the Linux kernel memory model. So how would it work? We're getting more towards the parts we want to talk to. I'm going to go through this reasonably quickly because I want to allow time for discussion. But at this point, I'm going to start going through a little more carefully. The thing is that we have multiple tools. We want to use the right tool for the job. There's something called HERD7. This is the original Linux kernel memory model that hit the kernel in 2018. It requires hand translation to its little litmus tests. It's exact, exhaustive. KCSAN is dynamic and approximate, but it is very good. I use it often to find problems in RCU code. It does require some integration with BPF. We talked about this a little bit last spring, and I'm having a little more detail on it here. One issue that's still kind of open is handling of user space components. That we may have to use some fallbacks for that, but that's hopefully part of the discussion. Okay, I'm not going to go this in detail. This is just I went through some of the tests and made a BCC-based, BPF lib-based build myself. And here are some of the translations you would use to hand code it. Again, I'm not going to go through this in detail. If you're interested, you can talk to me, or for that matter, to Andre, who has worked with us fairly heavily in his ring buffer work last year. Okay, and this is just an example of some code that's been simplified that you use as a starting point. This is the corresponding litmus test. If you run it, you end up with something like that. And the key thing here is never, which means that the bad condition never happens, the condition being here. So again, if you're really deeply interested in this, which I would encourage, talk to me or talk to Andre, again, who has used this. Okay, let's take a look at KCSAN. That's a bit of a newer topic. There's been thought about LKMM and BPF for a couple of years. KCSAN is more recent, but very useful. And if you want more detail, this URL at the bottom is notes from the meeting back in last spring. And the 2 relevant articles are also extremely valuable. They give a good idea of what KCSAN is, what it does, and so on. So what the basic technology behind KCSAN, kernel concurrency sanitizer, is software watch points. And this is kind of like hardware watch points. So what happens is the software detects conflicting accesses to a given variable. And this is used to detect data races. That was the original intent of KC-SAN. It's since been augmented, so you can specify what your concurrency design rules are. And we'll talk about that a little bit later. If you have in-kernel C code, BPF helpers, for example, those are already taken care of. KC-SAN already works with those. You don't have to do anything. But the JIT code can use the KC-SAN public API. This is an example of the API, basically where you do a read or write to a shared variable or something that might be a shared variable. You emit function calls as given by that pattern. You could directly call KC-SAN check access, and that works, but it doesn't give you as good performance. You could make this work with BPF trace too, as far as I know. Again, user space code, the user space components in a BPF program require special handling, and that is still, well, maybe we can discuss that here. Okay. KC-SAN can be tailored. In the main kernel, we have the values chosen for these first three kconfig options. Okay, so that is, if you just do a plain write, it assumes that's as good as a write once. I'm not on board with that, but there's a lot of people like it, and it's at least a way of getting them to put up with KC-SAN, which is a step forward. Also, if you have a write that doesn't change the value, KC-SAN doesn't complain about that. And it doesn't worry about interrupts coming in and making changes. Alternatively, RCU doesn't like those. I don't like those, so I make them strict. And there's Marco gave me a config KC-SAN strict, which reverses the sense of these three and also takes care of any other things that might be added later to soften the memory model. Okay, so you have some control over the types of errors or the types of races you wish to detect. And of course, it's going to give you stack addresses. We'll see a quick look at what it looks like when it gives you the splat in a little bit. And you'll want config debug info equals y and maybe some other things as well. You guys know the tools better than I do to more easily trace and the stack traces back to the source code. Okay. This is an example KC-SAN splat. You see a whole pile of equals sign, kind of like lockdep. And then you got this bug KC-SAN. It gives the two functions. In this case, it's the same function in both cases. And this is data race. And it gives you stack traces and state. And it didn't fit on one slide, so we've got the first one right here. So we have a write. It says the virtual address it wrote to, says 4 bytes, task 0 on CPU 7. And it gives us a little stack trace. And again, you'd probably want to translate that. I didn't bother here. It says there's no locks held. If you're running locked up, of course, it gives you a bunch of information about what's going on. It gives an IRQ event stamp. In other words, how many IRQs are there, which can be useful in looking at multiple of them, seeing how many interrupts happen in the meantime. And then it tells you when interrupts were last enabled and disabled, and soft IRQs last enabled, disabled. This is very useful in cases where interrupts got enabled by mistake and you're trying to find out where the bug is. On the next slide, we just see the dump for the other side of the race, which is a read. The previous one's a write. Stack trace is similar, and we have a similar set of things for the hard IQs and soft IRQs and the IRQ stamp. And then it tells us the CPU, the PID, the name of the thing, and gives us some information about the kernel, and it also some information about the hardware, which in this case, it was RCU torture running, so it's QEMU. So that's an example splat and what you can get from it. That can be a lot more useful than having something strange happen and trying to figure out, why is this strange stuff happening? It tells you, by the way, did you know this read and write are happening at the same variable, same time? And if that wasn't intended, you can track it down easily. We can also do it the other way. I mentioned earlier that you can encode design rules and tell BPF about your concurrency design rules, and here is how you do that. Okay, there's something called assert exclusive access. So if you have a situation where you believe there can be no racing accesses to this variable, you say assert exclusive access in the name of the variable. And then if there is an access, a read or a write on some other thread or an interrupt, it'll yell at you. Okay, so it helps flag violations of your design rules, where the design rules are specified by assert exclusive access. There are, of course, some cases where it's just fine for people to be reading, but it's a problem if somebody else is doing a racing update. And for that, we have assert exclusive writer. And that will not complain about reads, but it'll complain if there's another write. So if you believe that this piece of code is the only thing that should be updating this variable at this time, throw assert exclusive writer in there. And again, KCSAN will yell at you if that design rule is violated. Okay, and kind of a which is which kind of a thing. We have these two tools. We have the Linux kernel memory model, which uses HERD7 as a tool, and we have kernel concurrency sanitizer. And as always with these things, it depends. The Linux kernel memory model is very thorough. It does the moral equivalent of a full state space search. All right, so if a race could potentially happen in geologic time, Linux kernel memory model is going to find it. All right. KCSAN is only going to detect problems that actually occur in testing or that nearly occur. It does some tricks so that nearby reads and writes get detected, but you have to at least give it a near miss for it to notice that there was a race. It detects races that happen. Unlike LKMM, it does not detect potential races. LKMM, you got to hand translate, and you're very restricted. Your litmus tests have to be small. I mean, we're doing an exhaustive full state space search. On a good day, that's merely combinatorial explosion. On a bad day, it's undecidable, okay? So LKMM is doing something very hard, and you have to get a very small little program fragments for it to be able to do its job. KCSAN, on the other hand, takes the whole kernel, very happily eats the whole thing, and also deals with things like unbounded loops, function calls, interrupts, and all those other things. Those can be emulated in LKMM at a cost of analysis time. And both of them have different ways of checking for complex conditions. So if you want a soundbite for which to use, I would argue that Linux kernel memory model is a design time tool for checking the core concurrency design of your code. KCSAN is useful for regression testing. You've got the whole thing, it's there. You can run tests every week or every day or whatever, and it'll check everything for you at that time. Whereas trying to run Linux kernel memory model on your code every week is going to mean a lot of hand translation. Okay, that's kind of the introduction. I'd be open to any thoughts. One thing, I guess I'll kick it off with a question to you guys. I took a look through the test code for the BPF lib style BPF programs. And it looked like the user space components were mostly doing control setting at the beginning and then reading things out. And that's kind of nice in the sense that the concurrency of that is restricted and easy to handle. So I put the question out, what kind of concurrency models do we have for the user space components? My guess is sooner or later we'll get into the full up where it's doing closed loop control all the time. But I figure I should ask where we are now and where we're going. Any thoughts on that? Please turn your camera on, unmute yourself and all that. If Come on, I know some of you guys are not on Pacific time, okay? Of course, I know some of you are on even more disadvantaged time zones, but here we are. Okay, any questions or thoughts on other topics? Or do we have a fair amount of time we're giving back to people, which is okay too, I suppose.
Well, I think it wasn't clear to me, at least, whether this is the last slide and you're really opening up for the discussion, or...
Oh yes, this is the last slide. I should have said that. I've gone through the material, so it's discussion time.
All right.
The other option is if I've blasted through something too quickly, please feel free to tell me to go back and to go through it more carefully. That's legit too, obviously.
Well, I had a question about the exclusive, assert exclusive access. So it looks like only the assert exclusive writer is used by the kernel, and whereas the assert exclusive access is only for the. Oh no, yeah, I found it in RCU. So yeah, RCU is the only user of this, right?
Oh, I was the one that requested it, so that might have something to do with it. But yes, RCU does use both of them, and it's been useful to me because there have been times when I thought I had gotten exclusive access in my design and coding, but hadn't quite, right?
Right. So I was just thinking how this primitives can be used from the BPF side. So all the maps data is potentially can be shared and RACI. I guess we can have a special helper in some way to mark this kind of access with these primitives. But I haven't looked at the implementation. Do they guard like reads and writes are happening as a special instructions, or what's the details of the implementations here?
I'm going to give you my take on it. Unfortunately, I didn't think ahead and get Marco involved, and they scheduled him for a conflicting talk, so he can't be here until maybe the last 5 minutes. But what happens is that the kernel concurrency sanitizer, when it sees a potentially RACI access, it flags that internally, and it also randomly will do a bit of spinning to open up the race window. Okay, and during that time, it checks for similar instrumentation in the other threads, the other tasks, other CPUs, and complains if there's a collision, if it sees the same address, an overlap, if you will, between the two accesses. And so its normal approach is just to instrument the reads and writes in that manner. And what you're doing with assert exclusive access is you're not actually doing an access in instructions, but you're saying, okay, you're just asking the question, are there other accesses? That's assert exclusive access. So it does the same thing as if you had done an access, but instead of doing the access, it just does the random occasional wait spin, and it does the checking on the other threads to see if that variable is being either accessed in the case of assert exclusive access or written in the case of assert exclusive writer. And I believe that Marco has plans for additional scoped things where you can, maybe these are in by now. I should have asked him, but there are plans for making it so you can say from here to here, there better not be an access or write to this variable. So in some of the BPF programs, there are shared variables, and one approach would be to make assert exclusive writer and assert exclusive access available to the BPF code for to allow the writer, the developer of that code, to do similar sorts of things. Would that make sense?
Yeah, that makes complete sense to me, especially now we have a BTF tag facility on the LLVM side, so we can just, instead of using the macros, we can probably just annotate those variables and regions of memory as exclusive access, and the rest of the infra verifier in the JIT will do the right thing, whatever is appropriate.
Cool. Yeah, that would, ease of use is even better, right? Cool.
Paul, I'm not sure you have a chat open. There are a few questions in the chat. Or
no, I don't. Let me fix that. Go ahead. Why don't you pick the ones that are it's taking forever to, it's giving this little circle spinning. So why don't you pick them out and ask them in that way?
So Will is asking, does exposing the kernel memory model via BPF mean that we are unable to relax it in the future for fear of breaking existing BPF programs?
I'll give an answer to that, a prototype answer. Obviously, your BPF guys own this, but my suggestion would be to treat it the same as a kernel module. If the BPF program is in the kernel, then if we change the memory model in such a way that the code needs to change, we change it. If the BPF program is external and there is any kind of change in the kernel, in other words, we got a BPF programs out of tree, and there's any change in the kernel, be it memory model or anything else, it's the responsibility of whoever's maintaining it out of tree to modify it as needed for new versions of the kernel. So that's my prototype, that's my suggestion. And obviously you guys own the thing. And Marco points out, finally it got it up here. Marco points out, thank you, Marco, that sort of exclusive access is using K-free to detect use after freeze, which is kind of cool, but it does it indirectly. Okay, and let's see here. I saw quite, Eric Doomsday. Okay, I saw a question and I couldn't find it again. What's the scope of assert exclusive access and list splice RCU? If you just using assert exclusive access and assert exclusive writer gives you point-wise scope. I mean, just right there at that point, it's checking. It kind of opens up the window randomly. Obviously, if it opened the window all the time, it'd be painfully slow. But at random points, it randomly chooses to open or not. And if it opens, there'll be a time period, but the time period is still, at that point in code. What I'm going to do is I'm going to type to Marco asking about the scoped approach. Is there to be a scoped assert exclusive? Okay, and hopefully that'll get there. Will just Will likes my prototype response. Lawrence says, how could we write BPF that works across multiple memory models then? Okay, so what my assumption is you've got a user space code that is trying to use, say, the C++ memory model or the C memory model, and you want it to interact with the kernel. I would say that if you have a BPF program user space component that's interacting directly with the kernel, it's going to have to adapt. It's going to have to know that it's dealing with the Linux kernel memory model in those interactions. And so the one way to make it easy would be to have a full memory barrier. I mean, you could either use the Linux kernel model SMPMB equivalent in user space code, or you could put in something like a memory fence, a memory thread fence. I've got the name wrong, I'm sorry, but the thing there, and give it an SC memory fence. And Marco said that we've already got assert exclusive scope. Thank you, Marco, great. And so Eric, if you want to make a larger scope, Marco's already got it for you. So we're good there. And okay, if I miss somebody yell. I'm just gonna go through them again as I see them. So we got, then we got Kumar asking, are there plans to support consume control dependencies in BPF MM? Some building with Clegg front end and verifier recognize such accesses. That'd be a wonderful thing. One of the things that needs to happen is to make it so that we have, and control dependencies, both control dependencies, I'm gonna make a shameful plug for Will's, mostly Will's, also mine, Peter's and Jod Oglov's talk on, I think it's Friday, about the control dependencies. Well, we'll talk about those. The address and data dependencies, the consume dependencies would be their address or data dependencies. And we have proposals in the standards committee to handle those. And one of the things I need to do is get my act together and come up with some way of prototyping them in real compilers. We had a GSOC student a couple of years ago who got a good start. The difficulty is that what you're having to do with these things is suppress, selectively suppress optimizations. And the optimizations are kind of pervasive, especially in GCC, which has a interesting architecture. courtesy of Richard Stallman. So that's a general problem. It's not just BPF, it's everybody. And I need to make better progress on dealing with that. But it's a great question. Gotham, is it possible to convert some of the assertive loss of exclusive assets writers conditions in the BPF user code to an exist condition and do a state space search for the BPF user code? Given the BPF user code is expected to have bounded state space, can we use that to our advantage for full formal verification? Quite possibly. One of the projects that's kind of been in halfway done state for a long time is to analyze the primitives used by a given architecture in the Linux kernel and look at them, compare the hardware model for that given architecture, the hardware, formal hardware memory model, to the LKMM and make a determination if the primitives are sufficient. And this is not an easy thing, and it's been kind of going along slowly. But in general, anything we can do to automatically convert things is great. The one limitation we'd have to be careful of is that you can easily create something that's way bigger than HERD 7 can deal with. Again, HERD 7 is doing a very difficult thing. It's doing a full state space search, complete everything. And it's, you know, if you give it too much stuff to look through, it's never going to get done. But so I would guess that another thing that would be important for that approach would be some sort of slicer where you could say, okay, here are the parts I really care about, and have it automatically generate for you, and that'd be cool. A similar thing might be possible, be really cool, by looking at the warn-ons and bugs and other complaints, you know, assertions in the Linux kernel, and you know, having some kind of automated help to create a memory, a litmus test, a LKMM litmus test from that code. Again, slicing of some sort would be really important in order to make sure that the litmus test was sufficiently small. So, good question. So that's some good discussion. Other thoughts, other aspects that need some consideration? One thing I'd like to, I mean, Will, on the previous question about the change to the memory model and the BPF programs, Will seconded my suggestion, but then of course, on the other hand, Will is one of the LKMM maintainers and a core kernel guy. So we definitely would tend that way. Any thoughts from the from BPF folk on the status of out of tree BPF programs? Again, the proposal is if you have an out of tree BPF program, you need to look at each kernel revision. In other words, if you move from, I don't know, 5.14 to 5.17 sometime in the future, you need to look at the kernel and see what changed, if anything, and update your BPF program accordingly. Is that reasonable? If it's not reasonable, what can be done to help people? You know, would there be? Go ahead.
I can try to answer. I think it would be a default assumption for many already, mainly because that's a state of tracing world right now. When things depend on the kernel, they do break from time to time, and people do have to adjust their BPF programs all the time from kernel version to kernel version. In tracing, that happens pretty much every release. So LKMM changing from one release to another, though unlikely, if it ever happens, well, yeah, the folks will have to adjust.
And one thing I suppose it became too much of a problem if there ends up being tons and tons of BPF code out there, perhaps something like the printf change recently. Maybe there could be something that looks at a program and gives you suggestions about what might need to be adjusted. Easy for me to say, I'm not volunteering to do it.
Yeah. So we were saying that it could be subtle and hardware dependent breakage. That's, well, certainly true.
But that's also true. I mean, if somebody were to put some, I don't think they would, but if they were to put some trace point, a BPF trace point on some internal function within RCU, and I have to redesign it, the function goes away. I mean, that's life already. Oh, that one's easy to check for.
I think the extending KC-SUN to cover JITted programs, it would be the good enough solution that will cover all of this, majority of the subtle breakages. Right now, we're not there. And actually, my question was, if I understood your presentation, that's the teaching JIT to how call into KC-SUN public APIs for this read-write is the only thing that is necessary, right? So it will handle the races between one program accessing shared memory and another BPF program, just like the race between BPF program and the kernel.
That's right. That's right. The only thing that's kind of difficult at this point would be races with the user space components. So, for example, there's one that from what I can tell does it right. What it does, the user space component says, "Hey, here's my PID," and just stores it using the now I forget what it's called, but there's a data structure that's generated by the BPF system.
Right.
So
I think it's back to the Lawrence question of mixing different memory models, the user space and the kernel difference. So we have this problem already, and two ways of communicating between BPF and user space: the perf ring buffer and the BPF ring buffer. The fault certainly goes through this concurrency issues. That's why we have all the primitives ready for user space and the best practices of how to use these ring buffers.
So let me ask a question. I apologize for my ignorance of BPF as usual, but it looked like the user space program was just doing a store and that was reflected in the kernel. Was I misreading the code and it's actually going through the ring buffer somehow?
Depends. Maps would be just direct load store, just a load source action. Then the ring buffer, you're not, well, depends again. Like the perf ring buffer will do a copy, but well, depends and depending on circumstances. And the ring buffer will be just a direct write into the shared.
The ring buffer is easy because it has to be fully synchronized. Right?
Yes, so that's.
And I know Andre put a lot of effort into making sure it was fully synchronized. So that one's good. I mean, so if we're using the ring buffer, then the question becomes an easy one, which is anytime you use a ring buffer, it's fully synchronized, and that ring buffer then provides the interface between whatever user space memory model you're using and the Linux kernel memory model. If I wasn't misreading the code, and there really are cases where the user space just goes and stores into something that the kernel can just directly read. And you can do that. You map it, right? You do an map, and there you are. You got memory that's shared between kernel and user. That can happen. It's supported. Then the question becomes more interesting. And to Brendan's follow-up, the thing is, if we change the memory model, it's not just BPF programs that are getting hurt. We have to look at the kernel, right? 35 million lines of it, or whatever it is this year. So believe me, you're not alone in the subtle breakage. That's if we're going to change the memory model, we're going to be very, very careful how we do it for that reason. But probably not careful enough. That's life. So let's see. Paul says that outside tracing, and Will reinforces that the breakage is going to be difficult. Paul Changyong suggests that outside tracing doesn't happen often, and there's very large programs might have complexity issues. Very large programs might be some things that are being proposed to interact with Linux kernel networking and scheduler potentially. And BPF initializations happens before object load, he says. Okay. And there's a window issue. Okay, and by the way, Marco is here, And so actually, if people are interested, Marco mentioned that there was a assert exclusive scoped. Would you be willing just to say how that works, Marco?
Hi,
There
can
we
you
go.
hear me? Yes.
I can hear you. Very good. Thank you.
Yes, so I think that was also part of the first KC Sun release, and basically what it does, similar to the normal KC Sun, so the assert exclusive, basically it just starts checking an access for the entire duration of a scope. And you just use it like, I guess, similar to the other assert exclusive, but you add it at the start of a function, for example, then it will check the access provided to the macro until the end of the very function. And you can think of it a bit like simulated reordering of an access, which is actually how I'm planning to implement modeling weak memory with KC-Set, which is not yet in mainline, but hopefully I'll send the patches for that soon.
Thank you. Look forward to seeing those patches. That'd be really cool. It's probably someplace in RSU I should use something like that, although I'm not sure. I bet there is. I bet that. So let me ask a question. If I were to say acquire a lock and then release the lock, can I just put a curly brace right after the lock acquisition and a closed curly brace right before the lock release, and then do a scoped access across that and have that say this thing had better not change during this critical section?
Yes, you can do that.
Oh,
but
okay. I bet I can find some use for that. Cool.
I think like if you wait for the changes that introduce modeling weak memory, I don't think you even have to do that. So any access within the critical section will just be considered for simulated reordering automatically, unless it's, say, a release, S&P store release or something like that.
Okay, so to the example again, what you're telling me is with the new patches, just the fact I acquired the lock and released it, if I didn't have any memory barriers inside of this thing, it would just automatically scope all the accesses. That'd be really cool. Very good. Thank you.
You're welcome.
And scheduling is an issue here, but I'm glad Marco could make it. We have a couple minutes left. Bouchon mentions that he doesn't think we're going to relax the memory model, and I have to agree with him completely on that. Almost all the agitation at this point is to strengthen the memory model. The cool thing about that is if there are some weird corner cases that academics have come up with, okay? But as a general rule, if you strengthen the memory model, whatever worked before works afterwards, give or take some very strange corner cases. So hopefully that makes for less concern. The place you get in trouble there is if you create a BPF program for the new version that has a strong memory model, then try to backport it, okay? So the advice would be to write the BPF program and debug on the oldest version you're ever going to use it on and forward port it if memory model issues were of concern. And Lawrence mentions that versioning the memory model from BPF side might make sense. In other words, every time we change it, note that and then have the verifier give a warning, which, yeah, that especially if we had some change that weakened it. I don't see Linus accepting any change that weakened the memory model, given his stance in the past. But if he did, that would be a great way to help with that. So that's a good idea. Thank you, Lawrence. Anyway, any other questions, thoughts, concerns? I'm not too confused. We're right at the end of time. So if there are no further questions or thoughts, of course there are, feel free to email myself, Marco, or any of the BPF guys, or maybe all of us. And thank you very much for your time and attention. And hopefully this is KC Sans as useful to you guys as it has been to me. Enjoy the rest of the conference.
Thank you, Paul, so much for presenting. And as you said, yes, please reach out to any one of us for any further questions. So now we will have a 10-minute break until the next talk. see you in 10 minutes. Alexandra, you're a presenter now. Welcome back, everyone. We have 1 minute before we start.
Hello, everyone.
Hello. We can hear you well.
It's great since I'm on a mobile phone, working from mobile phone and also VPN tunnel. So altogether, what can go wrong? So I can switch the slides now, yeah?
I think, yeah, you should have all the controls. Yes.
Oh, yeah. Great, it works. Thank you.
Perfect. You can start whenever you're ready.
Yeah, thanks. So my name is Alexander Azimov. I work for Yandex, and today I'm going to show you how to enrich TCP with self-healing capabilities. Of course, in the case of network outage. I will start with the example focusing on the data center environment, but as you will see, it's not only about data centers. The minimal building block in the DC is a rack of servers connected to the top of rack switch. These top of rack switches are connected to the first tier spines. On this slide, S11 and S12 represent first tier spines. The set of top of rack switches connected to the same set of first tier spines represent a point of a data center or pod. First tier spines of selected pod belong to different lanes. Each plane consists of first tier spines and second tier spines or super spines that provide connectivity between pods. I will use literal X to represent super spines. On the top of rack switches and first tier spines usually used load balancing, and it uses a common 5 tuple, proto, source port, source IP, destination port, destination IP. So I think it's very, very clear. And on another side of fabric, there is, of course, another set of top of rack switches connected to its own first tier spines. It is believed that such topology provides both fault tolerance and easy scalability. Both statements are true to some extent. For example, if we increase the number of planes, we will increase network capacity. But it's really hard to do if you haven't invested in fiber in the day one. So modern data centers provide multiple paths between its points. The single path between two hosts exists only inside the rack. If we take a look at the interconnection between inside the pod, the number of paths will be equal to the number of planes. If we speak about interconnection between, not interconnection, but the number of paths between hosts in different pods, it will be a result of multiplication between number of pods and number of planes. So just to make you feel the numbers, here is a few numbers from one of Yandex data centers. It has 8 planes with 32 super spines. So we have one path inside top of rack switch. We have 8 paths in case of interpod interaction. And we have 256 paths in case of interpod interaction. One may expect that this number of paths should provide fault tolerance out of the box, but real outages in the DC are way more complicated. Let's say we have an outage and it affects one of our super spines, X11, and it starts to drop packets that are coming through it. If we're lucky, and our automatic tools, for example, BFD, are capable to detect the outage and drop down BGP session, everything will be fine. So the BGP session will be down instantly, and services will not notice any kind of service degradation. But if the situation is different and the control plane for some reason is not affected, we are experiencing a constant packet loss, and the situation is quite different. So since most of our traffic is TCP based, we need to rely on TCP loss recovery mechanisms in this case. And there are two common mechanisms. There is selected acknowledgement and retransmission triggered by the RTO timeout. But all these retransmissions will have same 5-tuple. So they will all travel the same path. And of course leads to continuous service degradation. And as the congestion window will be shrinking, it will increase the chances to meet RTO event. And continuous RTO events is a disaster. RTO is calculated as a minimum from a measured RTT and RTO mean. The default Linux value for RTO mean is 200 milliseconds. If we are unfortunate enough to lose a sync packet, the basic timeout is even higher, it's 1 second, while real RTT in the data center is less than 1 millisecond. To make it even worse, it increases 2 times after each unsuccessful attempt. So how this problem can be addressed? There are 2 types of active actors in the data center. There is, of course, services, and they may try to do their best. They may try to tune some TCP options, may try to create software health checks on top of TCP. Unfortunately, what proved from my experience, these tweaks and tricks are not that effective, and what more important, they do not scale. And if nothing happens, what do service teams? Of course, they blame the network team. And unfortunately, from some of my experience, at least in our company, I learned that some maintenance of services really think that this how things are done in network teams. The real situation, of course, is a little more complicated. The classic way is to develop both white box and black box monitoring tools to detect anomalies. The discussion about black box monitoring will take another hour, so let's focus on the timing. It takes a couple of minutes to collect data and process data. And after it takes another 5 minutes to verify it and isolate the broken device. As a result, it's from 5 to 20 minutes of service degradation. And it's global service degradation that affects all the services in the data center. And what a surprise, it still doesn't look good for the services. So what is the best way to resolve dependency between network and service degradation? How to make services use unaffected paths in the data center? And we have many paths in the data center, while giving the network engineers enough time for troubleshooting and isolation. And the funny thing, solution does really exist, and to find it, we need to carefully read few commit messages in Linux kernel. So let's do it together. In 2011 was published RFC 6438, where was stated that flow label in IPv6 header can be used to balance encapsulated traffic. It was not only for the fabric, but it was just a general case. The idea was simple. Since the transport layer is not available, we can improve load balancing quality if we put the hash from the TCP socket in the outer header that is accessible by the network devices. In 2014, it was introduced in Linux kernel, and also it was affecting not only flow label, but other types of encapsulation. For example, in case of GRE, it was affecting GRE key fields. In case of UDP encapsulation, it was affecting UDP source port. But the progress in Linux kernel haven't stopped at this point. It was progressing far beyond IETF documents, because it is the edge of what is writing at the IETF. The next year, there was another patch in Linux kernel, which added TCP hash recalculation upon negative routing event. What is negative routing event? It is 3 RTO timeouts. The next year, this behavior was further strengthened. Since this time, the hash is recalculated on each RTO and seen RTO timeouts. And finally, in 2018, there was also added support for the hash recalculation at the receiver side that is triggered by the duplicate segments. And as we discussed, RTO timeout now affects not only the flow label value, it affects all kinds of encapsulations. And a surprise, it have already become the Linux default behavior. So how does it change the life of TCP flows in the data center? And it is interesting, because let's once again have the same scenario. We have an outage and X11, it's partial, it drops subsets of packets. This time we also add flow label into our hash function of our top of rack switch. And in case of selected acknowledgement, nothing really happens. But if there is RTO timeout, the hash is recalculated, the flow label upon this hash is also recalculated. And so we're getting a 50% probability to jump from the failing path, to jump to another plane. And the more planes we have, the higher is the chance that we will be moved without TCP session interruption to unaffected part of the network. And it is fully transparent for the applications, so it looks rather great. And the last problem is RTO timeouts. As we discussed, they're huge. The RTO mean, it looks like it is accessible from the user space, and with the IP route tool, you can change it for selected prefixes. But a SYN RTO is different. It is nearly hard-coded in the kernel, and the only way to access it, so you can't access it from the user space, is using BPF. To find an example how to change it with BPF is rather simple. So it's just here. One may easily imagine here how to extend this example to cover, for example, proper prefix lookups. But let's take a look how it works all together in a real experiment. So we decided not to wait for a next big outage, but to create a small artificial one. So we took a real top of rack switch with real services and servers inside it, and real production traffic. And we created a packet loss on one of 4 its uplinks. On the left side, you can see the result, the outcome of our UDP-based data plane monitoring tool. It shows just that we have 25% packet loss. It's simple. On the right side, you can see the disruption that happened with service traffic. The traffic volume dropped 4 times. Now, the same experiment, but with a flow label enabled at the top of rack switch. The UDP-based monitoring tool shows just the same result, because it's just UDP pinger. It has no information about retransmissions and RTO timeouts. But the service traffic not affected at all. So the TCP sessions are just jumping from the failing path and finding the part of the fabric that is not that is unaffected, and everything is just looks great. So what one can learn from these slides: using flow label at the level of top of rack switch and first tier spines give TCP over IPv6, of course only over IPv6, the self-healing capability. To make this jump of traffic quick enough, you should use BPF programs to change both RTO and SYN RTO according to your latency. And this goes for free, though with poor documentation. And one may note that an environment with multiple paths is not limited to the data center. One may say that the internet itself consists of multiple paths between majority of its points, and all this jumping from failing path to another may improve user experience in general. Here are again some real numbers from Yandex. Less than 40% of prefixes that we are receiving from our peers have only one best path. The average number of best paths is about 4. The maximum number of the best paths that exists simultaneously is 44. So it gives a lot of room for jumping from failing path to another one. And here is a real outage. So it was affecting not our direct peer. So we had 5 alternative best paths, and only 2 of them were really affected, while the packet loss at the affected path was nearly 100%. So if everything is that great, so we have already in place flow label, we have hash recalculation, what can go wrong? Unfortunately, there was a trap. And this trap is called Anycast. In the DC environment, stateful Anycast services are not that common, while in the wild internet, Anycast TCP proxies are representing significant portion of traffic volume. These proxies and stateful Anycast services doesn't perform well with Linux flow label mechanics. Let me show why. Let's say we have a client that establishes a TCP session with stateful Anycast service, for example, TCP proxy. And everything is fine until RTO happens on the client side. In this case, the client will recalculate its hash value, and so does the RTO, so does the flow label. As a result, subsequent packets can be redirected to another instance which won't have an appropriate state and will drop these packets accordingly. There might be following RTO events that finally return the traffic to our original instance. But anyway, it won't improve the user experience. The scenario for the SYN RTO is a bit more complicated. Let's say again, we have a SYN packet, and it reaches one of our Anycast instances. And this time it's successful, but the response is not. In this case, when we are losing a SYN ARC, we have 2 sides, the server and the client, trying to retransmit its packets. So after default SYN RTO timeout, which is normally a second, the client will send another SYN packet with a new flow label, and it may reach another instance. But now we will have 1 client and 2 servers trying to establish one connection. So we have a race condition. If the SYNAC is received from the second proxy, everything will be fine. But if we receive it from the first one, we are meeting a peculiar situation. The client needs to send an ACK to finish the connection procedure. But it has flow label that directs packets to the second proxy and acknowledgement a number related to the first proxy. Of course, such scenario will end up with a connection timeout. So if you in your operations have experienced more timeouts in IPv6 compared to IPv4, now you should know why. And this is no theory. We have experienced this kind of problem with our own Anycast service. So in our case, it was layer 4 load balancers. To make flow labels safe, at least inside our own network, we had to do several workarounds. First of all, at the host, we set with using eBPF TX hash to 0 by default, which prevents it from recalculation. It is paired with explicit hash randomization for traffic that is destined to everything except layer 4 load balancers. We also had to disable the use of flow label at every device except top of rack switches. But all these fixes are no more than a temporary solution because the industry as a whole is moving in a different direction. The Service 6 is getting momentum, but it will effectively once again remove the opportunity to read the transport headers by the devices. So flow label hashing is becoming interesting default behavior. And whatever you do inside your own network, it won't prevent the user TCP sessions from jumping between your points of presence. So it gave us enough motivation to start looking for general solution. First, we started a major redesign of our Anycast services with focus on the layer 4 load balancers. We decided that we want to remove state from there, and maybe it's a good talk for another year. But we also started looking for how to change the Linux defaults to the safe mode. Well, of course, we wanted to preserve these wonderful capabilities of self-healing that we were already using and thought that they are very, very important. So we made a next observation. All issues with RTO and SYN RTO may happen only if hash is recalculated on the client side. And this provides an opportunity for a quick fix that will save improvements in case of outage and resolve the issues with TCP session timeouts. So we just restrict hash recalculation upon RTO events at the client side while keeping current behavior for the server side. It may become a proper default behavior. And of course, we love knobs. We want knobs to both to enable it in all cases or disable, who knows. This observation was partially addressed in the recent patch by Tom Hebbett, who suggested restoring the old default, where hash was recalculated after 3 RTO events. It may solve the problem with TCP connection timeouts at the client side, but decreases the opportunity at the server side, of course. Nevertheless, the patch also made hash rethink configurable, which is undoubtedly a change for the better. I believe that defaults can still be slightly different. I suggest to restrict hash changing at the client side unless it is enabled at the socket options. At the same time, we don't see any effects of side effects from enabling hash recalculation upon first or each RTO event at the server side. we are planning to send an update to Tom's proposal later this week. So, in IPv6 world, TCP transport was enriched with self-healing capabilities. It seems to be widely used by several big brand companies, but we still have an obligation to make it safe in general, and so to change Linux defaults so that it will not disrupt TCP sessions toward stateful anycast services. And this time, learning from the mistakes, we need to properly document it. By properly document, I mean document it at IETF. So that's all from me for today. If any questions, I will be glad to answer them.
Thank you, Alexander, for the awesome presentation. It was really great. Let's wait a few minutes for the folks to ask questions, if there are any. I don't see anyone in the chat. Please, folks, don't be shy. Oh, Eric has something to say.
Yeah, I'm not sure about changing Linux defaults, right? Because Linux defaults were changed years ago, so it will take time anyway to get the new default being applied on the majority of Linux hosts, right?
Sure. You're totally right, but the problem is that it will be increasing. So at the moment, for example, when we removed flow label from the hash function at the border routes, it was quite enough to stop users from complaining. But as the IPv6 adoption will be increasing, plus SRv6 will be, I believe, widely deployed, we will have this problem growing from year to year. And of course, we can't change the behavior of lots of hosts for a long time. But if we start now, maybe in a couple of years, we will have less complaints from the users. I hope I asked or answered your question. Lawrence?
Hello. Thank you for the talk. I missed part of it, I have to admit, so maybe you've covered this. I'm sorry if this is a stupid question. So it's interesting because I work on a stateless layer 4 load balancer at Cloudflare, and we have an Anycast network, so I think we probably face similar problems. And we've been having this discussion where there's kind of this anecdotal evidence on the internet that there is like bad middle boxes on the internet that will sometimes mess with your flow label, like clients connecting to you, to your edge. And then in the middle between, the person connecting to your edge, there is a bad middle box somewhere that will change the flow label between the SYN and, subsequent acts. Is that something that you've encountered at all, or something that has been a problem for you as you did this work?
Thank you for the question. I do not think we have seen such behavior from the middle boxes. We've seen the behavior when the client side was changing the flow label, and it was resulting that the TCP session was ending up at another point of presence without any state. So that was the problem. So about the flow label, if it can be changed by the middle box, of course it can be changed. unfortunately. It's not immutable, and it was every time it was stated that it is not immutable. But what, as far as I understand, it is not what such behavior is not common, at least, and I'm not sure that I understand the use cases where the flow label is changed. And according to the current ITF documents, it's mostly discouraged, but the ITF documents are quite confusing in the field of the flow label.
Yeah, I'm not sure there's a use case. It was just something that we found in a blog post, and so we've held off of using flow labels for this kind of for load balancing purposes. So it's interesting to see your experience. I put the link in the chat if anybody's curious. But thank you for your talk.
Yeah, great. I'll check the link. Thank you. Any other questions?
Well, I have a BPF related question. So, what do you think should be the features that you find that, like, what can you suggest can be added for in the BPF side where it overlaps with the networking for this specific use case? Like, you're already using it to adjust RTO, RTO, like anything else that comes to mind?
So the first thing that comes to mind that the opportunity to configure the hash thing should be part of BPF configuration, because finally we are ending up by configuring the server behavior in the DC environment by not changing the socket options at all applications but by using BPF programs and for the C groups. And we are for what I was saying and telling that we are planning to send an update to Tom's proposal, and we have already verified that hash rethink in our proposal can be enabled and disabled from the BPF.
Got it. Makes sense.
I hope so. So if there are no more questions, I'm going to say once again, thank you for listening. Thank you for your patience while suffering from my Russian accent. And hope to see you all one day in person.
Absolutely. Thank you again so much for the presentation. I really enjoyed it. Okay, we are on a break now for the next 17 minutes. So the next presentation would be defragmenting the loader landscape by Timo. And we'll be back at 8:40 Pacific time, which is 17 minutes from now. Enjoy your break. Hello, everyone. I think we're back on time. And Lawrence and Timo, your stage is yours. Go ahead.
Thank you very much, Alexei. I'm going to kick off. My name is Lawrence. I work at Cloudflare, and then Timo is going to also present the big chunk of this presentation. And we titled it Defragmenting the Loader Landscape. We had a hard time coming up with a good name that kind of encompasses everything we want to talk about. So this is really about Timo's part, which I think is very interesting and exciting. I'm also trying to go to the next slide. There we go. What is on the agenda? Part one is going to be a bit of marketing about Cilium eBPF and what it's used for, what it is in the first place. Part two, I'm going to tell you about an idea that I have to make generating UAPI bindings for other languages easier. And then finally, Timo is going to talk about his idea to make loaders more integrated and to be a better citizen, even better citizen in the community, I should say. So let's get started. First off, what is Cilium eBPF? What is it? What can you do? Some of you might have been at previous Plumbers, of course, and we talked about this there, but it's worth reiterating. So Cilium eBPF is a eBPF library in pure Go. It's maintained by us, Cloudflare, and Cilium. It's really easy to distribute. There's no dependency on the C compiler. It's easy to cross-compile. And I would say that we focus on what I think is a good name for this is like fat user space eBPF programs. So things that get loaded into the kernel where there's lots of logic in user space that needs to happen. And finally, it's MIT licensed. This is to preempt questions that invariably tend to come up. Why do we do this in the first place? And I think there's like loads of nuance to this topic, as we saw yesterday in the talk from the IR Rust people. I think one of the strongest arguments is that Go has a fat runtime, and this means that the foreign function interface, which is called CGO, is significantly slower than syscalls. It's hard to distribute, makes binaries bigger, and it's just not a good experience to work with it. A couple of use cases that Timo has collected from people that have contributed to the library, and then we've reached out and tried to figure out what they're using it for. First off is runcn and containerd. Some people will know this. It's used by Docker and Kubernetes to execute containers, and they use secret device filters. Next up is what's called Datadog Agent, and they provide observability for workloads that run on machines. We have Intel with a thing that's called the CRI Resource Manager, which is a really cool idea, I think. They use BPF to track how much AVX 520 instructions I think a workload executes. And then depending on how noisy it is, it will move those workload away from other workloads. We have Palantir that kind of do a more classical tracing style use case. And they have a cool talk that you should watch, which kind of goes into the details why they do it and how. There's also Hetzner Cloud. They do some contract limitation using K-probes. There's Microsoft with a tool that is called Inspector Gadget. It seems to be like a Swiss knife for Kubernetes applications, as far as I understand it. Second to last, there's Cloudflare, and we have a lot of stuff kind of written in XDP for DDoS mitigation. We have a layer 4 load balancer, control planes of various kinds, and we use the library extensively. There's also some open source code that you can look at if you'd like to. Now, finally, we have Cilium. And Cilium is a container network interface implementation for Kubernetes that has some really advanced features that are very heavy users of BPF and all of the tooling that it provides. Now, in my work on the library, we kind of so far have generated bindings for BPF syscalls by hand. So whenever a new feature was required, I would go and, or the contributor would go and look at the source code of the kernel and take the struct and manually convert that. But it's kind of tedious, it's error prone. And instead, it would be a nice idea to just take the VM Linux BTF and write out Go types and functions. At the bottom, you can see what that would kind of looks like. So there's a function to make the syscall and some attributes that are embedded in the struct. And there are, of course, challenges to this. The Go type system doesn't know unions, which we have to deal with. And the runtime also has a garbage collector. What does this mean? We need to make sure that we tag every single pointer in the types that we generate correctly. Otherwise, the garbage collector can go and free things behind our back, and then our applications will crash. There's also no explicit control over whether an object is allocated on the heap or the stack. I want to go through some examples of things that I found difficult while generating the types, or the bindings, I should say. On the left-hand side is what is currently in BPF.h, and that should be familiar to lots of you here. There's an enum that defines a couple of flags, and then we have the big union BPF attr, which is passed to the BPF syscall. The problem with this is that there's no way to easily refer to the enum or this struct that's embedded in the union from BTF because I don't have a name. And I think the kind of, if I were to say, oh, how could we fix this? The obvious solution is to just add a name. So we give the enum a name, and we kind of add a new struct that has this map create name, for example. I'll keep using the same layout, where on the left is what's in BPF.h right now, and on the right is a suggestion what we could change to improve the situation. Next up is preprocessor macros. I think on Monday there was a talk about this already, where it's clear that they aren't present in the BTF, so there's no way for us to ever generate from them. I think a pragmatic approach is to switch over the remaining flags to enums. There's also the issue of invisible pointers. That kind of goes back to what I mentioned earlier with the Go having a garbage collector. You can see on the left, there's this structure which in it has a path name field, and the type of that is aligned U64. This is just a way for the BPF user space API to say this is a pointer that is always 64 bits. It doesn't matter whether this is running on a 32-bit architecture or 64-bit one. The problem with aligned U64 is that it doesn't really end up in the BTF. It just looks like a UN64. So we can't automatically tell where these important pointers are. And because remember, we need to kind of tag each pointer, otherwise the garbage collector will go and do nasty things. On the right-hand side, you can see what we could replace it with. There's already this cool macro BPF MD pointer. I think that means metadata. And on the bottom, you can see that this is just equivalent to a union, where there's this pointer type, and then make sure that this field has the right size and right alignment. Finally, my favorite part, I think this is what I call field overloading. And there's a struct, and it has a comment that says, used by BPF star get star ID. And whenever I read it, I kind of, in my head, I have to go and do like a mental pattern matching. I've done the work for you. So on the right-hand side, you can see what actually the different commands take. I want to draw your attention to one thing, which is, I think, the most interesting, which is that this map get FD by ID actually has a field next ID, which is completely ignored by the syscall. And to me, that was not at all clear from looking at the type definition in BPF.h. I had to kind of go and look at the implementation. And I think my argument here is that the structure on the left that we have is hard to understand both for machines, because we can't generate the correct types, but actually it's also hard to understand for humans. And that's something more like it was on the right-hand side, where kind of for individual commands we have individual structs would be easier. A quick recap, and that's also going to be the end of my talk. I think we can simplify BPFH for robots, and we, in the same instance, also make it easier to use for humans. And we can use enums instead of macros. We could give types and fields a name. We could use the BPF metadata pointer macro. And we could also have one field in BPF Vector for each BPF command. And I haven't tried all of these yet, but I think that they can be made backwards compatible, of course. That's it from my side. If there are any questions, I'm happy to take them now. And then afterwards, Timo is going to take over from me and talk about the loader landscape.
Well, since we're in the middle of the talk, I will just give my quick few cents here. I think totally makes sense. And all of the issues you pointed out with BPF.age, well, real and worth fixing.
Cool.
And Paul is saying all of the changes to BPF.age would also make it easier to detect necessary updates for traces, caller, etc. Yes, I agree as well.
Cool. So I have my work cut out. I think Paul has a question. Oh yeah, there we go. That's what you just read. Thank you. Okay, I think my next step would be that probably sometime next week I might start sending things for the easier bits, like adding naming enums, stuff like that, and then see how far I get and ask people to give feedback. So thank you very much.
I think Florian was still typing a question, but I'm not sure if it'll come through. If it's okay, then I can get started. So my name is Timo. I work at Isovalent on Cilium, and I also co-maintain the Go library presented here in this talk. And today I will talk about integrating alpha loaders, or how we can align second party, so to speak, better with libbpf. Full disclosure, this is actually Martina's idea. I was looking for a way to present something like this, or actually present a solution to this for a while now, and then he floated the idea a few weeks back, so well, here it is. First, let's sketch out the loader landscape, how it is today. So we have libbpf. Sorry, when we say loaders, we say solutions or projects that actually implement their own elf loading natively, like non-wrapper projects. There's a bunch of these in other languages as well. But just for the sake of the argument here, let's limit ourselves to this list. There's obviously libbpf, Cilium eBPF, and then IRS as well, that was presented yesterday. But last but not least, also eBPF for Windows, which cannot look at GPL code as far as I understand. So they might also benefit from the solution that's going to be presented here. Of course, features still land on libbpf first, because it's the upstream solution, like it's the blessed implementation, of course. But there's no real straightforward way for other projects to verify whether or not they're compliant with how libbpf does things. So, of course, the question is, how could we align these projects better? A few years ago at LPC 2019, it was mentioned often, like from crowd interactions and also in the talk itself, that libbpf is considered to be the spec. And that's all fine and well, but how do we actually codify this? Without having to go look at the source code, well, we might have to end up doing that anyway, but without really reading and understanding the source code of libbpf and like cheating to see exactly how they're doing things, how could we codify this as a bit more of a contract instead of a convention? So maybe instead of a vague spec, let's write some tests. Bit of background first. The compiler communicates with the loader through ELF binaries. And existing loaders like libBPF, BPF tool, and historically also IP Route 2, but they're now also since migrated to libBPF a few months back. They expect ELF, so eBPF, ELF binaries to follow certain conventions. A very basic example of this is ELF section names. So legacy map definitions always went into the map section. BTF maps now go into dot maps, and for example, the program attached type is attached as a string, prepended as a string to the section name. Of course, as time went on, the eBPF feature set and also the ELF contents and just the complexity of the BPF subsystem grew more complex, and the loader had to follow suit, obviously, to cater to this. So now, how do we verify that ELFs get correctly parsed and that none of its contents get ignored? For example, when a new ELF section is introduced by, let's say, BTF, not so recently anymore, it's been a few years now. So how does a BPF program that's been loaded into the kernel tell that all of the sections were taken into account? And how do we ensure the loader stays compatible with older and newer kernels, older and newer LVM versions? Also frequently causes some regressions. How do we verify compliance with the BPF itself, since it's considered the spec? And then also, which is, I feel, a bit of a recurring theme here at LPC, how can Linux maintain control over the toolchain end-to-end and keep everything compatible, compliant, and a bit uniform in the ELF format, for example, or just the way that eBPF works. Obviously, eBPF programs that only work with loader X or Y are not ideal. Nobody wants this, especially not us. Like, we just want everything to work regardless of which user space, language, or runtime you're using. And it's also a bit considered that more loaders equals more ecosystem fragmentation, but maybe this is not fully the case. So today, the Linux kernel ships with a set of self-tests, and they basically verify all the components in the toolchain: the compiler, the loader, the kernel, and they test a wide variety of behaviors end to end. And building them results in user space programs as well as BPF ELF objects. So as we see here, xdping is the user space executable that actually gets run by the test suite. This executable will pick up the object xdping_kern, and it will load it, parse it, and then execute all the actions that is expected to actually get maps created, load the program into the kernel, perform relocations, etc. There are a few problems with this that we found working with this from Go. Besides the BPF programs themselves, as I mentioned, the self-tests also require a specific user space code to load and exercise them. They're all specific to the particular BPF program, so there isn't one program that can load all BPF ELFs, let's say, and execute them in a uniform fashion. That's just not the case. They're all separate. They're all discrete test programs. They're quite often complex. They set up arbitrary net devices, addresses, send packets back and forth, etc., just to test kernel and loader behavior end to end. And there's simply too many to replicate in other languages, especially when working on smaller teams. If it's just a few people working on a loader project, then there are no development cycles to implement all of these, make sure they're kept up to date, bug-free, etc. And so there's no way to verify if the loader's resulting bytecode is correct, even when it's accepted by the verifier. Some core offset might be wrong, like it might be within bounds, but it might not read at the right offset. It might be off by 1, by 4, by 8, who knows? And as I mentioned slightly before, unfortunately, the self-tests also exist to exercise behavior of the kernel itself specifically, not just the loader. And if you're writing a loader project, you only really care about, is my project, is the software that I'm writing is it doing the right thing? The second problem that we're running into when, maybe I haven't mentioned this, but the Cilium eBPF project builds all the self-tests that are sitting in the kernel tree, and we load them, but we don't execute them. And we're running into the problem where self-tests are added to the kernel tree, but they're meant to be invalid, like they're intentionally invalid. They serve to test the negative behavior, like you write some invalid instruction, then the loader is supposed to error out, or the verifier will return an error. And the issue that we're having is that they're not really named consistently to reflect this fact. So we basically have to resort to ignoring them or ignoring errors on specific tests. In this case, I've included a small snippet here. So for example, these two core tests, we ignore errors when we load them into the kernel because they're just built to fail. So in our opinion, another approach is needed. As I mentioned before, the self-test elves are parsed and loaded but never executed. So there might be subtle bugs that we currently simply cannot uncover. So we would like to propose unit tests that target the user space loader infra in isolation. So without relying too much on kernel behavior being there. But I'll outline this in the next few slides. So since all loaders, let's say, that exist today, Rust, Go, and libBPF as well, the common factor between all of them is, of course, BPF. So could we possibly craft BPF programs that test themselves at runtime? The answer is yes, we can. We have a few examples of this. So as a few basic principles, we should try to build eBPF programs that contain useful line info BTF so that the verifier output is clear. Okay, I'm receiving bytecode here that doesn't make any sense, and then the line info would explain a bit why, maybe using macros or comments. They can contain runtime assertions, so reading particular map values and comparing them using immediate comparisons. For example, also making sure if the right map access has been relocated into an instruction. And then, as I mentioned before, also checking if core relocations have been executed by reading some known good values, like some a struct somewhere that contains bytes 1, 2, 3, 4, and then making sure at runtime that we're reading the same values in. This could generate error feedback by reading the verifier log or BPF prog run, or a combination of both. Another requirement for this would be, of course, a minimal user space surface. So a program, basically a loader program or a testing program that's devoid of any business logic and only interacts with the most simple, the BPF APIs. This would make it easier to port to other platforms or languages. And for example, it could just find elfs on disk using a glob of some sort, invoking the loader that loads programs, maps, BTF, performs necessary transformations, just does everything in the background. This should not be part of the test suite itself. That's all the loader's job. Then, for example, it could load a program. If it doesn't pass the verifier, it could display what the verifier log is. And then if the load does fail, it could call prog run on all programs in ELF, and it would succeed if the test returns 0. So what would this actually look like? There's a few examples that we have in the Go project, so in Cilium eBPF. For example, on the left for static data relocation, based on different qualifiers of this variable, so uneg is a volatile const, and in C code we assign it the value -1. And depending on the qualifier of the variable, this will end up in a different ELF section. But still, later we execute a program that makes sure that using an immediate comparison, like uneg needs to be equal to -1, neg needs to be equal to -2. If it doesn't, it will sort of generate a runtime assertion, so the return value of the program will not be 0. Same for core relocations. We expect these types to be core relocated into the BPF program. If it's not the case, then it would just generate a runtime assertion and the test would fail. Sorry, runtime exception. So what would be the next step? So we suggest an independent loader test suite that is separate from other end-to-end kernel or eBPF self-tests. So for example, we could submit a new test loader test suite to the Linux tree, just to have all the test code centralized there. And other projects like Cilium eBPF or Aya could build these self-tests in CI or pre-build them like we do now, and then basically just run the loader against them and see what happens. If everything passes, then that means the loader is doing a good job. This would also allow us to iteratively agree on a common set of behaviors that all loaders must implement. Maybe from day one, we could just have basic features, how to load an ELF, perform basic relocations, relocate maps into programs, etc. And then over time, we could expand this to basically absorb more and more functionality. A reverse example of how this could actually benefit the Linux project upstream is a feature that we landed recently in Cilium eBPF. So Cilium makes heavy use of tail call maps. So we would like to populate these from C code by statically declaring them. And we got inspired by libBPF's map and map declarations. So instead of passing map pointers here, we pass program pointers, and then the loader will hook this up at runtime. We'll create the map, load all the programs, put all FDs into the right indexes of the map. And if this kind of behavior would be accepted into a loader test suite, then this would kind of signify a contract or an agreement that all projects that aim to implement an ELF loader would adhere to these standards. So I probably hear you thinking, why do we have non-BPF loaders in the first place? And this has been discussed over and over. So maybe the first point will not vibe with many people, but having a standard test suite would make it easier to bootstrap other loaders in other languages, might cause new libraries to spring up, and maybe something using a different API or focusing on a smaller subset of BPF. This would be made easier by removing the burden of creating a project like this. So basically, they just have to implement ELF parsing, prog load, prog run syscalls, maybe loading some BTF as well. And then they could iterate from there to support more and more of the test suite incrementally. And in our opinion, this might potentially reduce fragmentation in the ecosystem because there is a shared goal. There's a shared target, like these are the behaviors that we're all going to adhere to. And ideally, there would be no deviations whatsoever. And everything that would be supported in libBPF would also be eventually supported by all other projects that want to implement the loader. I think that was it. Maybe there might be some questions, maybe not. We'd be glad to hear them. I think the activity in the matrix chat pertains to Lawrence's proposal. So maybe we can answer those now if needed. Sorry, Alexei, go ahead.
I was just waiting for anyone to jump in. I have questions
Right.
of course, that I was waiting.
Yeah, go ahead, go ahead.
To throw forward. Well, on my side, I 100% agree with the problem statement. I think the gray area is how much this Rust, Golang, and C loaders cause the fragmentation and whether it's a good or bad thing. I think collectively we can think of many pros and cons to this loader competition at the same time, but obviously it causes the fragmentation and inconsistencies, and what is being produced is divergent. And this is just looking at Linux ecosystem, where kernel is common, and on the other side the LVM common, and in between we already have like 3 different loaders. With Windows in the picture, we have completely different kernel, and I don't think they use L format for loading, so that could be yet another problem. Plus, like loading on non-general purpose CPUs like Internet Random NIC, that's a bit different, though it goes through the hardware and through the system call, so the surface problem is somewhat different, but absolutely, I think it's definitely the problem to internalize and try to address.
Yeah, maybe something else to add here. There's been, I think you sent some proposals for creating a BPF-based loader, which is also going to be new code. It's not going to be libBPF, I assume. It's going to be something from scratch, maybe using another bytecode format that's not ELF. But having a shared test suite could also help developing that by making sure that if a new loader project grows within the kernel tree, is that going to be compliant with libBPF? Or any of the other loaders out there could be, historically IP Route 2 as well. It's been a very huge, it's been a very big factor also in the history of BPF. I don't know. It could benefit more than just the existing contendants. Again, I don't see them as competition because they bring in developers from other ecosystems as well. Me personally, I'm not a C programmer. I love working in Go, so that's been a positive adoption factor for me to start working in BPF, because I wouldn't be very comfortable writing user space software in C. So if I prefer doing it in Go, then it's just an added force, right? It doesn't really. I agree generally that it disperses the development effort a bit. And so our efforts people might think, yeah, we all need to be focused on the BPF, but I see it more as a multiplicative effort instead of detracting or competing per se. Maybe we need to sort of change our stance on this a little bit over time.
I agree. I think the freedom of language choice should be preserved, right? There is no point convincing people who love Rust to, not to use it, or love Golang or C++ or any other language for that matter. Also, the thing I forgot to mention is that GCC now almost reaching LLVM feature parity in terms of producing the code, but I'm not sure what kind of ELF format they generate and whether it's compatible with LLVM. Also, there are DSL languages like BPF Trace that don't use libBPF at all, and yet they load all sorts of stuff. And you've heard the AOT talk that sort of replicates this loading problem again. And so, yeah, you mentioned that I've been working on this loader program concept. So the rough idea, it was for signed BPF programs, but not only. Like signed, I would say, is 50% of the goal. That's getting all loaders into some sort of common ground is another part, and a big part of this effort. So that ideally, the loader program would be, currently it's partially complete. It's, I would say, 50% there. And it's currently done mainly by libBPF that generates this loader program that can be used out of Rust, out of Golang potentially, with exception that Rust is always multi-ELF, multi-compiled unit, and it has additional linking step at the end. So there are all sorts of complication, I think, in terms of building an ecosystem that where the loaders are uniform and the languages and choices of the language don't pose this challenge to the users whether their program, if they're writing it in C, would be acceptable, but if they're writing in Rust, it won't be loadable only because loaders diverge.
Yeah. I don't know what the alternative would be in terms of a spec, as it was mentioned multiple times before, like libbpf is a spec, but it's also growing astronomically, and replicating more and more of its behaviors grow. I mean, it gets quite tricky.
Just like Golang loader, right? So you just
Yeah.
mentioned the tail call feature that doesn't exist, and I'm sure the Rust AYA is in some ways a similar. Like it got the BPF linker before BPF got its own linker, and now we have LLD patches for LLVM LLD that also can do the linking in a different way. The
How
is definitely
does that
growing.
work today then?
I think the right answer to this is standardization. In more, but how to standardize, it's always, of course, a question, right? So like one way is to say like, here's a spec, here's a document, and another is to write the tests. So I think test is will be more correct and precise. The conformance tests for what is like loadable and what we expect to be loadable is probably the best. So what you're describing, like all of the slides, I completely agree. Just curious, what are your thoughts on the next steps here?
In which sense?
Like,
As in where to go from here? Or...
Yeah, like how to build this loader tests.
In terms of process or in terms of governance, because those are also two different things. Initially, we could start out contributing what we have in the Go test suite, like in our test data, writing a C program that does basic libbpf interactions, just reading an L from disk, letting libbpf perform all transformations that it has to, and starting out there. Just starting with the basic behaviors, as I mentioned, like loading a few programs that don't contain too complicated features, maybe some static data, simple map relocations. It can just, I see it as more of proposing a framework first and then iterating on this over time. Also, as features are added to libbpf or to the kernel, to kind of grow this test suite along with the development of BPF itself. Does that make sense?
It does.
As an example, let's take the features of BPF 2 years ago and start there. Like no BTF yet, no core maybe, just simple BPF. From there, adding on more and more features, also as we agree on what the behavior should be, because libbpf does things a certain way today, and I'm sure we would all like to adhere to that, but that's a process, right? Encoding that in a test suite is a process.
Right.
It's not going to happen overnight. Yeah, and there's also the added complexity that Daniel hinted at, is how do you involve every project like AYA, Cilium, libbpf itself, like everyone would need to collaborate on the mailing lists and vote like this is how we're going to do this feature or not. As in it becomes more of a governance matter, or how to include and bring several projects together. And yeah, we're just going to have to figure this out as we go over the months, years to come, I think.
Yeah, and don't forget the skeleton adoption that's currently growing. Just plain libbpf loading is kind of a thing of the past in many ways.
That's what I wanted to say, that like your premise is that like let's test on the loader part, and sure let's, but like in real applications, like look at the libbpf tools in BCC, for example. Like there is pretty much no tool that doesn't do some runtime adjustments, setting of the parameters and all that stuff. So I would be curious to see how it actually looks like in practice, because just saying like, oh, here are like few programs and few static variables and maps, and let's just test if the loader loads them, that's a little bit too simplistic, I think.
But we need a starting point.
But we need to have a plan as well.
Yeah, of course. But there, you mentioned it's not really like, okay, you say BCC, there's programs that do runtime adjustments, but it's not about which adjustments to make, it's about how to apply them, right? That we need to encode in this test suite.
Now, my point is like you have some read-only variable, like read-only from the BPF perspective, right? BPF side code. But it's not read-only from the user space standpoint, right? And you're saying, let's write some like universal user space part that would magically just like set everything up. And I don't see how this magically will happen. Like we can always say like, oh, let's cover this specific use case, add some more conventions, how you specified from inside the BPF so that user space can read that and apply it at runtime in user space or something like that. But that gets pretty ridiculous pretty fast. So it's a good starting point to cover some of the features. I don't think we will be able to cover like the entire ELF loading space with this approach.
I think we would get quite far, and I'm also only proposing interactions that can be embedded in the ELF itself, so that wouldn't include map operations at runtime, for example. It's only the transformations that happen between loading an ELF from disk and inserting it into the kernel. That's where it should stop, in my opinion, initially.
How familiar you are with BPF skeleton, for example?
Not at all, but I've used our own.
So please take a look. Yeah, it's a major part of any modern BPF application, pretty much. So just take a look at that and think how we can test that, because I think that's important. And I'm also curious, like, what's the equivalent of the BPF skeleton in Go is, like, especially for the global variables, actually. I think, like, for Go, it will be a little bit harder because you cannot just, well, maybe you can, but, like, you will need to generate, like, the struct that has the same memory layout as like the kernel side of the BPF program, and then let user space have direct memory access to that. So that's an interesting, like, besides all the testing, I think that's an interesting feature that would be good to have like in every language.
I want to point out the comment that John Fasterman mentioned in the chat that lots of real applications don't use skeleton, and they do adjustment after ELF parsing and before the final loading, for similar reasons that skeleton users like adjust the global variables before the final load, or just like map max entries during the loading process.
Yeah, maybe I can. So Andrei, if you're curious, there is a thing that's similar to skeletons called BPF to Go. And it's, of course, inspired by your work. And it kind of goes in a similar direction, kind of do code gen to embed an API for making it easier to work with object files, basically. But what I wanted to maybe step back and ask is, because Alexei, you mentioned that kind of Windows eBPF is probably not going to use ELF. I guess my slight tangent is it desirable for there to be an eBPF binary format that is standard across platforms, or do we think that, like, I don't know what the answer is, or is that not a goal that you should pursue?
I think it's a good goal to have in mind. Whether it's achievable, that's a big question. At least, like my own itch is the loader program. I was hoping that it will be just like single map and single program. So 2 blobs of bytes, that's it. And in addition, a generated Golang, C, and well, eventually like Rust wrappers to interface into the global variables the way that C skeleton is currently doing. This to me looked, at least like I imagined it to be like platform independent, and will cover like multiple languages, and we'll be able to test all of them. While
I actually don't see a problem for eBPF for Windows to use ELF for BPF object files. it's not like those object files are directly loadable into Windows, right? So it can be ELF. Why not?
And
Why
Yeah,
not?
just
Another-
I thought
Sorry,
maybe
if we-
what Andrea was saying is that it wouldn't use Clang to emit stuff. I'm not sure what you were trying to say.
Again, why not? Like, what's wrong with using Clang? So I think like the whole
no,
BPF
no, it
object
depends.
file path like can stay the same for Windows, right? Like the only part that will be different and incompatible is user space. Like, well, if that's the goal, obviously, I don't know like what's going to happen, but I don't see any technical problems with that.
My question about inventing our own binary format is how much will it look like ELF in the end? Because it's just a container format, right? We would reinvent the wheel, and what would it gain us? The complexities of what we have to deal with today won't necessarily change. We still need to solve the same problems, it's just in a different container format. So I'm not sure where that will take us in the end. I also don't see why Windows couldn't use ELF or Clang for that matter.
Just, for example, why not Clang and why not GCC as well? Why not? Fine, not let Visual Studio generate this code, right? And also BPF Trace guys are working on having their own mini compiler that's not LLVM that can produce this code. And I think other projects I've heard have been thinking about similar.
I don't think we're going to get an answer on Windows's behalf during this session, so maybe that's to be discussed at a later date.
One thing I was wondering about, like longer time ago, like before you had the BPF loads, BPF proposal, there was also one where we were thinking to use the user mode helper and basically have like a binary that would communicate behind the syscall interface, and that could potentially be, it could potentially also be in a different runtime, maybe. I'm not sure like how feasible that is. I mean, it doesn't have to be behind the syscall interface, of course, but it would be nice to have some sort of a drop-in where you could then move like the different loader standalone binaries in that sense, and then like try to run self-tests with it eventually, so that you would iterate through them at least through the major ones, and see if things break or if they don't. I think one problem with that could be like you would have to implement exactly the same interface as self-tests use, like for the BPF C code, right? And that might not be practical. And yeah, I mean, overall, I think it would be nice to have like even RCI, like have different, like in the future, like running the test with LVM, like if GCC catches up, then also have an iteration with GCC, or like a different CI is spawned with that for all the kernel patches that are coming in. And that would be a dream, right? To see if things break or not.
By the way, on that topic, we've had support for GCC for years now. Like the self-test BPF makefile, when it detects that GCC supports BPF target, it actually builds a separate flavor of test progs for GCC. So we have like test rogues, no ALU32, and then GCC BPF. I don't know if anyone in practice uses it, but like it's there.
Yes. I mean, question is if anybody tried it out. Maybe the GCC folks, but they could probably clarify that.
Yeah, sounds like we won't be able to solve it in the last minute, but yeah, like as Timo put it really well, is the governance question and practical like approach questions. Like we need to start solving them. Whether it's a discussion should continue on mailing list or office hours, hallway hall, chat. Let's keep cranking on it.
By the way, if someone isn't following the chat, Alan, I don't know, he's probably involved in eBPF for Windows. He mentioned that they do use Clang and ELF for eBPF programs in Windows. So that question was resolved, I guess.
Perfect.
And also, I had a question to you guys, like for the Go library, right? Like, have you seen the libBPF 1.0? Proposal and sort of work, right? Like, even in your examples, you still use some of the section names, for example, that will be rejecting eventually. So it will be good for you to like at least follow along with that. And I do agree that we should try to keep as close as possible. I'm a little bit worried about like setting up all those extra committees and agreeing on every single small detail before even doing anything. Like it's what we can grind to a halt, like instead of actually making some progress. So like let's be just considerate of that, I guess.
Yeah, I mean, I've seen the 1.0 a while ago. I think I left some comments on it as well. You're right, I haven't followed up what's happened ultimately. I think in the best case, the thing that Timo described, which is like a separate, not separate, but just some way of identifying these are tests that we should be running or things we should be rejecting, makes it a lot easier for us to follow what libBPF is doing. And I'm not even getting into saying like, what's the governance here? I think that's a bit too much, really. So maybe it's okay to just do what libBPF does. I don't.
So like one of the examples in your like blacklist.
Sorry, I have to cut you guys off. We're out of time. The next presentation had to start. But let's continue off. Martina, see your presenter now. Go ahead.
Hello. Yeah, let me try to enable the camera. Okay. Yeah, so let's start, I guess. Daniel, are you ready? Yeah, cool. So, hi. So I'm Martinez, and today, together with my colleague Daniel, would like to present some interesting kernel issues which we found while developing Cilium DataPath. So we both are full-time Cilium DataPath developers, and in addition to that, Daniel is one of the maintainers of the BPF tree in the kernel. So let's start. So before we dive into the main content, I think it's good to have some background information on the Cilium DataPath. So in LPC 2019 and 2020, we talked a lot about it. So in particular about the load balancing component. So for this year, I think it's good to show some of the changelog since last year. So the main change is that the Cilium is no longer tied to Kubernetes, which means that it can run as a standalone L4 load balancer. And this comes with additional changes such as consistent hashing support, in particular maglev algorithm for backend selection. Then we have a PCAP recorder, which is used for load balancer traffic observability purpose. And then we have a DataPath extension for the health probing of backends. And the main principle of the LB, at least components, is that we want to try to be as close as possible to the socket when it comes to the east-west traffic, and as close as possible to the driver for the north-south traffic. And all our DataPath programs are running in the form of BPF programs, and we are basically using TCXTP layer, and in addition to that, the socket layer via C group hooks. Okay, so let's move on. So this talk is split into 4 unrelated parts. So first we're gonna talk about C group V1, V2 interference, which became obvious after some distros have enabled both by default at the same time. And then another thing is the TCP pacing in the context of the Cilium's bandwidth manager, which we talked a bit last year. Third, we're going to talk about some problems in terms of the L2 entries management and L3 entries lookups, which complicates not only the Cilium's data path, but also the control plane. And finally, we will talk about possible extensions of the BPF maps to support the wildcard lookups for the observability purpose. Okay, giving control to Daniel.
All right, thanks. So let's first start with the C group V1, V2. So here's a basic overview of a typical layout. So if you dump the SysFS C group tree on the vast majority of distributions, you will see something like that, where you have a long list of C group V1 controllers that are mounted, and then there's the unified C group V2 mount. And in order to add BPF programs, we of course have to attach them to the C group V2 root in this case. So on a typical host that runs in Kubernetes and where Cilium agent is loaded, it will basically attach programs to, like for the load balancing in particular in this case, to the connect, send message, receive message, get peer name and bind hook. And then basically it will do a DNAT. So whenever the application calls, like let's say connect system call, it will rewrite the socket address structures in the kernel so that you can directly hook up one of the backends. And recently, like one of the projects from Kubernetes side that got quite popular among DevOps and so on is called Kind, which is called Kubernetes and Docker. And here you can basically, the goal of Kind is to simulate Kubernetes nodes in your whole cluster basically on a single host. So your host here basically has Docker containers which represent themselves as a Kubernetes node, and you have multiple of them. And in this case, the C group mounts basically like their namespace, so they're still under SysFS C group for the container which has the Kubernetes node in particular, but in the initial namespace, they have a different subpath, of course. And yeah, so what the agent does in that case is it loads the eBPF programs, of course, to the root, in this case, to the SysFS C group inside the container, so that it's on the root from a Kubernetes node perspective as it was before. And in the initial namespace, there's nothing attached because that's basically out of reach for the agent itself. And to give some context, where now like the problematic bit comes into play here. So longer time ago, when the C group V2 was added, basically the V1 case had tagging information for the NetCLS and NetPrio controllers. NetCLS is basically, like the original idea was basically that you can move applications into this particular C group, and then all their sockets that they spawn have a specific tag that can be user defined, and then later on in the TC, for the TCQ disk, it would help the classification of the traffic. And similarly, the NetPrio, it's basically for giving a packet priority for that, also for the TC case in the end. And then later on, like when the C group V2 was added to that, the socket basically got another pointer to point to the C group V2 object. And in order to not bloat the socket structure too much, because of performance reasons, it was basically both put into a union so that we can, like in total, have only 8 bytes, and that's it. Yeah, but in reality, as you've seen, like from the different, like from the previous slide in the directory structure, it's very likely that both flavors are mounted at the same time. And how does it look in the fast path? So whenever we want to execute a BPF program, such as for the connect system call, like the socket C group pointer helper function will basically retrieve the corresponding C group V2 object. And whenever there's, like, because of this overloading, whenever there's tagging from the C group V1 in place, we basically have to fall back to the root C group of the C group V2. If you don't have to compile it in, well, then all is great, but it's not typically the case. And yeah, so why is this problematic for those environments? Well, because like if you have to fall back to the C group v2 root, it's the root in the initial namespace. So whatever is attached inside such a simulated Kubernetes node is being bypassed, and there's nothing attached in the initial namespace. And that basically means like an agent that is attaching something to the root for that Kubernetes node cannot do anything about it, unfortunately. So yeah, so it's like that management is basically complex and cumbersome because it's not compatible with C group namespaces. I mean, like with the non-C group path, it was kind of clear, but if you would attach to the root and then your namespace, you basically will inevitably run into those problems. There's also a trade-off that was made originally. So when you are already attached to a v2 and you have a reference to it and then switch later on to the v1, to the C group v1 controller, you will leak basically the C group v2 object references, which is also not that pleasant, but it was deemed acceptable back then as a trade-off. Yeah, so but overall, like this invocation, like there's always like a weak point where it's not reliable. Because like third party or other agents where you don't have control over in the cluster, they could step on like onto each other. And typically also like distributions, they usually enable, as we know, everything for maximum compatibility. So yeah, the approach that we took in terms of fixing this situation is basically to bite the bullet and to detangle both, so that in the end, like the C group data structure holds basically both, like the C group pointer and then like the legacy stuff. And hopefully at some point in the future, we will be able to retire it, but we'll see, yeah. Implicitly, this will also fix the read-to reference count leaks. So yeah, the fix has already been out and has already been upstreamed recently. But yeah, if you have any comments, I'm happy to answer questions around that. We can also do this at the end potentially. The next case that I would like to talk about is basically around TCP pacing for Kubernetes pods out of the initial namespace. Just to give some background on current state and what's possible. And in Kubernetes, basically there's a so-called bandwidth annotation. It's basically something that you add to the pod spec when you deploy a specific pod to your Kubernetes cluster, and you can say then, okay, like this pod has egress bandwidth of 50 megabits, for example, and enforcing this annotation, it's basically optional to parse it and to enforce it, but there are some plugins, some CNI plugins that can do it. Originally, there was only the bandwidth plugin, which is one of the official or maybe semi-official Kubernetes plugins. And we recently also added this to Cilium. And basically, the semantics is more or less defined by the implementation from the plugin. The Kubernetes bandwidth plugin, it's a really crude hack. It basically adds an IFB device for the ingress bandwidth enforcement, and then attaches a token bucket filter to that. Same for the egress, and I think, as far as I'm aware, it attaches this to all the Weave devices in the host namespace for the enforcement. We took a different approach, and we only implemented the egress bandwidth annotation for that, and basically the agent then from Cilium is attaching FQQDisk to all the physical devices in the host, and then it will use BPF to basically set the timestamp, and then with the earliest departure, like enforcement in FQ, like to enforce this rate limitation. So that's basically an overview picture here of what I just mentioned, and what you can see here above is like how the pod spec looks like in that case. Just to give some overview on the data path. So basically, we have a BPF program attached on the physical device, and then on the host Weave devices, and we use like the redirection out of the TC layer. There was a talk from last year's LPC for more details into that. On the way out, we basically use the FIP lookup, and then either like the direct BPF redirect or through the neighboring subsystem. And in terms of this enforcement, what what I just mentioned earlier, thanks to the fact that when traffic from a pod networking stack leaves is trying to leave the node, it will first switch network namespaces, and there the socket association is still preserved. And then the BPF program on that host weave will basically mark all the pods into a traffic aggregate, and the BPF program, once it's finally reached the physical device, on TC egress will basically set the SKB timestamp based on the rate limit that was pushed down from Kubernetes side into a BPF map, and then like the MQ and FQ leaf QDISC will then enforce it. And the socket association is still there until that point, which is great. And now like the next step that we would actually love to get working is to have a socket inside the pod network namespace define its own either max spacing rate, or it could use PVR as a congestion control algorithm, which also uses spacing implicitly, and then have this enforcement on the initial namespace and the physical NIC. And today it's basically not working because we have to reset the timestamp to 0 when we switch the network namespaces, and therefore like the FQ on the physical device cannot do it. And if you look at like if you would enforce a rate, for example, 4 gigabit per second, this basically looks completely unstable if you try and run netperf with that. And yeah, so it's not working. We did a POC hack in that sense, where we just tried to play around and try to retain the egress timestamp from the TCP stack of the pod, and did not reset it on the network namespace switch, and with that you get a nice stable rate. And like just the rationales and some background on why there is why this timestamp reset is needed. So basically the kernel uses different clock bases for the SKB timestamp. One is on ingress, where it uses the clock tie, which is the international atomic time. And on the egress side, we use a monotonic clock, and the same is for FQ. So basically, if you would not reset this, then the forwarding from RX to TX would basically cause a drop in the FQ QDISC, because it would overreach the drop horizon. So usually FQ internally does, I think it's by default maybe like 5 seconds, or you can also configure this lower to potentially 2 seconds. If a packet has a timestamp that is further out in the future to that, it will just drop it so that it doesn't have to keep it in the queue for too long. And right now there's no way to figure out like what timestamp is being used, and hence like this reset is currently needed. And the question is maybe like, can it be normalized to a single base? So like in the past, Eric and others, they tried to use the like clock tie as well for the egress timestamp, and there was an issue on the mailing list where someone reported with some weird embedded device that this broke their communication because like the real-time clock on that node was set up in a broken way, and then like when the node booted, I think systemd was like adding an offset for plus 50 years, and yeah, things break. So that's why like the egress side had to go back to a clock monotonic, and now we have this reset. So the question is, or maybe one proposal could be like to fix the situation where we could get this to work. What I like from the scenario earlier, to add a new bit to the SKB where we have like a timestamp base, and when it's, let's say 0, it's basically the clock basis as tie, and if it's 1, it's the monotonic clock. And we could have helpers to use that from RX and TX side, and the FQ QDISC could then detect that if the timestamp is not a monotonic timestamp, it would reset it to 0, and it would then implicitly like treat it as today, as if we would forward it, and otherwise it would just enqueue it properly, and then we could potentially remove all this setting to 0 upon forwarding, One thing that is an issue actually here is that the net timestamp check function, where we basically timestamp all the RX packets, it would have to be deferred after TC ingress. So like when we go into the local stack, it would have to happen at a later point in time. Yeah, are there any comments from anyone?
So the net timestamp check, is that what sets the timestamp if it isn't set by hardware as well?
Yes, exactly.
And why does it have to be deferred?
Well, otherwise, like when traffic crosses the network namespace from a pod, then we are basically back in the RX, like in the receive path, and we call the main receive routine, and there's like this net timestamp check in there as well, and it would basically override it. And in order to retain like a monotonic clock on the SKB, so that we can forward it from TC ingress all the way to the physical device, we would have to do it at a later point in time, I think.
Oh, so that you can get to it in BPF before it gets reset.
Yeah, exactly.
Okay. So that has a potential to slightly delay measurements of how long the packet was in the system, right?
Potentially, yes.
I'm not sure if that's significant, but that could be a concern.
Mm-hmm.
Otherwise, I think this sounds great to actually get this working.
I see Eric.
So yeah, I was wondering, this base of the timestamps, because we now have the new time namespace. So maybe a single bit might be not good enough. I'm not sure. If we want to allow, a container to have a different namespace for the time. So obviously, even the monotonic time would be different for this namespace.
Oh, I see. Okay.
So, but I'm not sure how it can be handled right now. I'm not sure if we have convenient helpers to convert, let's say, when a packet escapes from one namespace and enters a new time namespace, if we have a way to convert this timestamp into the the current namespace.
That's a good point. I did not take this into consideration at all. Yeah, I will look into that. How we could do that and issues with it. And I presume there's also no way like to have the other way around, to have everything in terms of monotonic clock and then convert from there to clock tie, right? I think that's probably not feasible either.
That I don't
know. Okay.
No, when the timestamping stuff was added by I don't remember from Intel, someone from Intel added that. Their proposal included some bits in the SKB to tell if what was the base of the timestamp. And for some reason we fought hard about adding new bits in the SKB. So I think that's a historical reason why we don't have this bit yet. But if there is some convincing case of why we need them, then maybe we should add them at some point.
Yeah.
Could BPF be responsible for converting? Like if you need to move the point of reset anyway, maybe we could just have BPF be responsible for converting.
So like, yeah, I mean, that's a good question as well. Like the initial hack that I did, I mean, I don't think it's upstreamable because it's way too ugly. You would still have to have some way to avoid clearing the timestamp when you scrub the SKB, right? And that's what's currently happening when you switch namespaces. So you would have to have some mechanism that's not too hacky to do that. And then, I mean, like the rest could be done from BPF, right? But like, I don't know, like.
Could BPF set a bit that disables the scrubbing? Or copy it into the CB or something?
I would love to, I mean, like, so my approach was I would love to avoid having to manage anything inside the pod namespace. So I don't want to attach a BPF program there on the Weave device in the network namespace and then set this bit. I would love that this would work without any cooperation between the pod namespace and the host namespace, so that the host can just deal with it.
But this always goes via a VF device, right?
Yeah.
So a flag
potentially other
feature
things
on VF.
Say again?
So could we set a bit on the VF device, telling us that we'll handle it on ingress when it comes out?
Could also be an option. I thought it was maybe too ugly, because how do you configure this? And it's quite implementation specific as well. Do we really want to expose this implementation detail to clear it or not clear it? And yeah, so it didn't feel clean enough somehow. Yeah. Anyway, like, in the interest of time, I will move on, because there's still other things to cover as well. But definitely it's a good discussion. So the next part that we have is on the L2 and L3 management for the load balancer. Basic idea, like the load, the Cilium load balancer and also other XDP-based load balancers. They're sitting in the middle here and get the traffic from switch with ECMP-based load balancing and then move it to a backend. Typically, the way it does, it's directed to a service IP import and then forwards it to a backend IP import, either through DNAT and afterwards SNAT, which we do in a kube proxy replacement, or DSR with IP encapsulation. But in both cases, really, like, the backend IP is the destination address. And we've been using the FIP lookup helper to piggyback on the neighbor resolution. And then in the end, the load balancer is pushing it back out through XDPTX. And right now, the neighbor resolution, I mean, what you cannot do is from XDP side, if it's not in the neighbor table, to suddenly start resolving and do ARP requests, because you cannot hold the packet. So basically, it already has to be present in that case. Right now, it's one of our pain points, and we have a hack in our agent where we resolve entries manually and then push them down as a permanent entry into the neighbor table, but it's not great, and it definitely has limitations. So how does it look like? If there's an event like from the Cube API server that a new node came up and it's one of the backends, for example, then it will tell all the other agents from Cilium side, and it will do the ARP ping, and it gets the resolution, it pushes it down. And it has to do it periodically. So right now, I think we do it every 5 minutes or so. I think it's also probably suboptimal. But the buggy case here is really that there's a small race. So when we have like an obsolete permanent entry for the node where the Cube API server is running on, and then like the Cilium agent would restart, and that Cube API server node L2 address changed, then you basically would lose connectivity, which is not which is horrible. And the other thing that it also doesn't do is like it doesn't automatically update for active traffic. Like when traffic comes up the stack, it's still like, because it's a permanent entry and externally managed, it's not doing that either. And it's duplication of the existing logic and so on. We need an equivalent for IPv6. So basically the requirements that we would have as a control plane is one thing we initially look up when the node comes up based on the IP address. We look up from Netlink side, the kernel, if the backend IP is in the same L2 address or if it's accessible through a gateway IP address. And then what would be nice is to push it down as an L3 address without the corresponding L2, and then let the neighbor table just handle the resolution. And in addition, to keep it in reachable state. Also to avoid garbage collector eviction, and then later on, if you have a restart of the agent would be nice to know like which of those entries were managed by the agent, so that it can clean up obsolete ones. One thing we can piggyback on, I was not aware of this earlier, but reading through the code, there's already an NTF use state or no, it's in UD used state, sorry about that, and a flag NTF externally learned. That would get us quite close already. So the NUD used state, if you push an entry down, it would do the neighbor resolution in the kernel already, but it would only do it once. And then it, if the entry gets stale, it would get updated back to reachable if there are external traffic events or internal ones, which require a new resolution. And because of the externally learned flag that was added, it ensures that we're not adding to the garbage collector list. But what it does not do, it's not automatically refreshing it back into the reachable state. And what we also don't do is like we don't propagate those creation flags back to user space. And they are also not retained on carrier down events, so as opposed to the permanent entries. So one of the design points here is that we could add a new NUD managed state, and it would be a volatile state, so it would not be, it would not stay there. It would change like into reachable, for example, and it would add it to like a per neighbor table list, so that there's like a delayed work queue, which would trigger the resolution periodically. And this could be combined with the externally learned one to avoid garbage collection, and also could be retained in the on carrier down events. So this is how it looks like. You would basically add it with the externally learned flag that already exists, and then NUD managed, and then here's what you would get back, and it would get refreshed automatically in reachable state. And given there's a bit of time issue, I will hand over to Martinez right now for the L3 bits, and we can do the Q&A in the end.
Okay, so let's move to one layer up. So in particular to the fib lookups. So in some situations in the Cilium data path, we need to determine a source IP address of a packet which has been modified by the data plane. So in particular, let's consider this example. So we have a pod client sending a request to outside, which needs to be masqueraded. And for this reason, we have a BPF program attached to TC egress, Cilium data path program, which is masquerading that request. And the if device on which this program is running has two IP addresses selected. So currently what we do in the data path is basically that we hard code the IP address with the agent. When it generates the program, it selects the IP address according to some heuristics it implements. And it works fine when the device has just a single IP address, but it doesn't work when it has multiple addresses. So yeah, in this case, the reply from outside would be probably a black hole. So what we want to do instead we would like to use the BPF fib lookup, and we wanted to set the source IP address if it hasn't been set before by us. And because this information is already available in the fib table. So we had, for this, we have a proposal extension, which we are going to upstream soon. So it's basically to add the new flag, basically saying that, okay, so if we don't set the source IP address, please set for us. And this is basically also nice, not only for devices with multiple IP addresses cases, but also that we, from the Cilium agent perspective, we don't have to hard code the IP addresses into the data path anymore, and they can be retrieved from the fib table. So another problem with the fib lookups is that in the case of multi-home networks, so in this example, we have a LB node, which is basically doing the service translation. So it translates the request. So it does DNAT to some particular backend it selects. And it works fine when you have one single interface for egressing those translated packets, but it doesn't work fine when you have multiple devices. And we have to basically, again, to replicate some logic of fib lookups in the data path to support this case. And instead of doing that, I think it's because this information is, again, it's available in fib table, we'd like to do, again, fib lookup. And if we don't set the target interface index, we would like the helper to set it for us when it returns. And actually, after closer inspection to the code, it seems to be the case, because there's this setting of the interface index. But unfortunately, if you don't specify the if index by yourself when you do the helper call, the check, which is above the setting, fails. And I think it shouldn't be the case when you don't set the BPF fib lookup direct. So again, we have a change, just a matter of cycles to upstream it. Okay, yeah, then Daniel, back to wildcarded BPF map lookups.
Okay, so that's the last topic, and then we can do a short Q&A afterwards. So the use case is basically on the load balancer to correlate inbound, outbound packets, and to have a recorder for that, so that you can introspect, for example, like the path taken from Fabric to layer 4 load balancer to layer 7 ones, proxies or backends. On the agent, there's an out-of-band mechanism where you can program this, and we have a component called Hubble where you can basically then construct a PCAP file out of the rules for that. There's unfortunately here we cannot play the GIF or so, but in the slides you can. There's a link to it where you can see a small demo. Hubble basically here, but also any other consumer of this API could specify a given filter, and then the agent internally will push this down into the BPF XTP data path. It will create a wildcard mask, and if there are multiple entries with the same sort of masking, there will be 2 users here. We'll keep track of this and then regenerate the data path basically. So how does it look from a flow perspective? So first we have this classification whether this particular traffic is subject to where we have a packet capture for that, and if so, it will store basic information in a per CPU cache, and push the original one into the perfing buffer, and later on it will the perfing buffer itself, it has some additional metadata like the recorder ID and then the PCAP header, but with monotonic time, and then the full or partial packet capture. And then later on, after the encapsulation, for example, we push it to the backend. We consult the per CPU cache whether there was a prior match, and then we push the corresponding egress packet out. So such a recorder consists basically of a source cider, destination cider, then source destination port. There can be 0 for any, or a direct match. What we don't support is a range of ports, and in terms of protocol, either any TCP, UDP, whatever, or a direct match. And then, as I said, the agent has basically an API that is exposed. It's tracking the different masks from the rules and regenerates the data path whenever there was a change in the masks. And then it uses a single v4 and one for v6, a hash table for the rules to look it up. How that looks like, super briefly. This is basically generated by the agent. So that's the set of masks. And whenever that changes, it regenerates it. Then it derives a lookup key based on the original tuple from the packet on the given prefix mask, and then on the actual on the target key that we then want to use for the lookup itself. And if there was a match, it holds basically some information about ID and capturing length. And this is basically how we generate this key for the lookup itself. But overall, it's just a poor man's version of a wildcard match. One thing that we assume is that the number of that the set of those masks is small, but overall what it would allow for nevertheless is a large number of matches that are within this mask set. So that's still acceptable for the use case that we have, but it's suboptimal because it requires expensive on-the-fly recompilation, and you also need to go and linearly probe for those masks. It works on all the kernels, but there's of course always the risk that things get too complex for the verifier to understand. And it would be nice to have a native wildcard BPF map in the kernel overall to have basically fast lookup time in the order of millions per second, reasonably fast update time. I think that would be totally sufficient if it's in the order of thousands per second. And going back on the mailing list, I think in 2018, there was already a discussion back with BPF and OVS where they wanted to implement megaflows in BPF, but that stalled a bit. We've been looking into recently, like what's state of the art in terms of the typical packet classification algorithms, and it seems to be like tuple merge is so far the best choice in terms of that's an extract from the paper here, but in terms of the classification time and also the update time. And even if you have large number of rules, like at least the simulation from the paper looked promising, but so far we didn't look into a POC implementation yet. That's going to be next on our to-do list. But yeah, it would be nice with that to solve this problem that we don't need the recompilations and so on. But if anyone has any comments or experience or like had similar issues and how they solved it, I would be super curious. And yeah, with that, basically opening up for questions.
Thank you, Daniel and Martinez, for the great talk. It was so dense, so much information in, in 30 minutes. Yeah, it was hard to follow. I have few questions. Can you go back like one slide, like first start from the last? Yeah, so for the this is great. So like it just might like 2 cents here that yeah, if we can get this any of these algorithms, whichever one is makes sense to implement given kernel constraints. Like not every user space algorithm is acceptable to the kernel, so yeah, the kernel might twist the dynamics of this applicability of the algorithm. But yeah, it would be like awesome, I think. But like as a first, but have you looked at the map for each helper instead of pre-generating masks?
Nope, not yet. I mean, like so far we needed this on a 5.4 kernel for the user which was running the load balancer in production, but yeah, for later ones we definitely need to look into that.
Yeah,
but overall I totally agree with you. I mean, it has to comply with RCU and all the other things, and not everything works, of course. Like yeah, the tuple search space algorithm was used by OBS. Tuple merge in the paper, at least they claim it's like the lookup at least seems to be at least 7 times faster, update times around 35% slower than TSS. But I mean, overall those are simulation results, so it would be good to have an experimental implementation and test it out how it looks.
David is wondering in the chat whether tuple merge is pattern encumbered.
Oh, that's okay.
This algorithm.
I have no idea. I mean, it was like the so the author of the paper and the so he's from academia, but to be honest, I haven't looked. This didn't cross my mind. I have to look into that to see like what's the state there.
So I have another question, if no one has any, regarding the NAE turbo management. So it sounds like to me that you appeal to have some sort of direct interfaces into NAE, but then I think the slides kind of went into that you don't really need any NAE manipulation directly, and everything is possible to do through this existing fib lookups. Did I get it right, or just this managed new state is enough?
Yeah, like so this managed state would be enough to keep the neighbor entry in a periodically in a reachable state. so that we can use it from the FIP lookup, and FIP lookup will then populate it for the XTP data path, right? Yeah, and like the existing infrastructure for that today, like with the NUD used state, which I think is one of the super old code that like came in from the earlier days, but like what it doesn't do is like it doesn't refresh it. Like if there was it doesn't refresh it by itself into the reachable state unless there's an external or like internal traffic event where you, I don't know, try to ping this node or whatever. But it would be nice to have this completely self-managed by the kernel, by the neighboring subsystem, because there's no need for any of that to have those external triggers.
And for the source IP selection, we don't need any neighbor entries, just to make clear.
Oh, yeah. Oh, there's a comment from author. Shameless plug, we compile CBPF to eBPF to do packet captures with libpcap, which supports matching on subnets port ranges. Yeah, I mean, like that approach is possible as well, but if you, let's say, have a lot of entries, like a lot of, let's say, /32 CIDRs, and so on, like I presume like this generated program gets really large pretty quickly.
And
so like yeah, like I mean, like in the case where you only have like the few set of masks where you would have this unrolled loop, let's say for, I don't know, 10 entries, whatever, but like you could have thousands of you could have thousands of hash table entries where you would then match those IP addresses of interest, right?
Yeah, you kind of end up trading map entries for just like actual code. So we do use this with like hundreds of entries, but of course there is a limit to the number of instructions and how many you can actually compile.
Right. And one thing we actually want to do is like move this from the load balancer piece actually into the Kubernetes, like into the actual CNI data path. And there we already have BPF code in there. It's complex, and then adding another thing that could bloat the code is like my biggest concern. There is the verifier that we will trip over it, and it will reject the program in that case.
Yeah, it makes sense. That's one of the challenges of generating eBPF.
Yeah.
All right, we have, let's do a 2-minute short break before the next talk. Thank you, Daniel Martinez, for the excellent talk.
All right, thanks.
Lots of stuff as usual.
Thanks.
Dmitry, you are a presenter now, and I think you should have control of your slides.
Yeah, let me check, please. 1,
We
2,
can
3. Do you hear me?
We can hear you, but we cannot see you.
Yeah. Yeah, I'm switching it on. Yeah, it seems that you now should be able to see me.
Yeah, perfect.
Right?
Yep.
Yeah. So shall we start?
Yeah, go ahead.
Okay, hi. I'm Dmitry Banchikov. I work as a software engineer, and today I'm going to talk about BP Filter, what it is, how it works, benefits it could provide, and what are the plans. BP Filter was introduced back in 2018 by Daniel Borkman and David S. Miller. It was described as a BPF-based replacement for IP tables. The presentation agenda is quite simple. First, we will review how IP tables works, and then we will switch to BP Filter, how it may replace IP tables and BP Filter's future. Let's jump to IP tables. So, despite the fact that NF tables is considered to be a successor of IP tables still in use and will be in use for many years more because IP tables has a large adoption among people. It is popular, familiar, and successful. And well, let's review how it works. So IP tables consist of multiple tables, such as filter, nut, mangle, and others. Those tables are consulted for various types of traffic. Each table has a set of predefined hooks, which determine at which moment each particular table is consulted. For example, the filter table has 3 hooks for input, forward, and output. Rules are grouped into chains, and which may call each other. They form a directed cyclic graph. Each hook has an attached chain. The fate of a packet is determined by checking rules until there is a match. Each rule consists of multiple parts, a set of matches and the target. The set of matches determines checks that are performed against the packet, and the target determines the fate of a packet. Here's an example of adding a rule into the system through IP tables binary. Here we see that -a determines to which hook the rule is added. In this case, the hook is input. -s determines the source address, source network in this case, -d destination network, -p means level for protocol, and -d port means destination port. And -j drop means here action to be applied for a packet. So the default table is filter, so this rule is added to the filter table. Let's take a look how those rules are stored internally in the IP tables and kernel. So a rule is represented by struct IPT entry. It consists of struct IPT IP, which determines a set of predefined matches for protocol and level 3 source destination addresses. Flexible array member at the end, a couple of service fields and fields that determine offset into flexible array member for rules, additional matches, and target. A rule itself provides a very limited set of functionality. Basically, it is possible to match a packet only by level 4 protocol and level 3 source and destination addresses. Here's an example. We see struct IPT entry placed somewhere in memory in this case, and flexible array member is substituted by multiple xt entry match structs and xt entry target at the end. Each of the matches determines one element from the rule set of matches. Each struct xt entry match contains a field match size that determines the offset of the next fields. Here they are. Field target offset determines offset to struct xt entry target that contains the target for the rule. Field next offset determines the whole size of the rule and defines the offsets of the next rule. Multiple rules are placed one after the other. Following the next offset field, it's possible to iterate over a block of rules. As I said earlier, basic functionality is quite limited. all additional functionality is implemented by external modules, matches, and targets. Those matches and targets are represented by struct XT-entry match and XT-entry target in the configuration blob. Those structs are quite similar. They have a union with different representations for user space and kernel. User space passes a name either of a match or a target, and kernel is responsible for placing a pointer to actual match or target inside the kernel. At the end of both structs, there is a payload that contains data used by match or target. Struct XT match and struct XT target define interfaces for kernel modules of matches and targets and provides a way to extend basic functionality of the firewall. Those interfaces provide a set of virtual functions to check copy to or copy from user and actually make a match or apply an action to a packet. Everything that is described on the man page, IP tables extensions is implemented by such either match or target. Rules in a chain are placed one after another. Chains are placed one after another, and the table has offsets into the blob for each of the hooks, which determine a set of rules that are executed for an attachment point in the kernel network stack that is determined by hook. Let's review how those rules are interpreted. So rules are interpreted in the following way. IP tables iterate through rules until there is a match. If a rule doesn't match, then IP tables proceeds to the next one. The first step is to match the rule's immutable part against the packet. To be more precise, level 3 addresses and level 4 protocol are matched against level 3 packet header. This is done by the function IP packet match. The match is performed in the following way. As you can see, there is no place for optimization. If a particular rule doesn't have checks for level 3 addresses, there is still a comparison and there is no way to skip it. The same thing applies for matches and targets. When iterating on a rule's matches, a virtual function is called for every match. Because the virtual function doesn't have any context, it must be written in a generic way without any possible optimization. Why optimizations are not possible here? Because those virtual functions must not assume any context. They have to be implemented in a generic case. That is why this design doesn't allow us to utilize some specific knowledge, either about a rule, match, or target. So effectively, a rule's interpretation looks like a set of comparisons which couldn't be skipped if a rule doesn't need them. For example, source destination level 3 addresses were not specified. For each match in a rule, there is an indirect call, and the target also may have an indirect call. Now, when we understand how configuration of IP tables is represented internally, let's take a look at the kernel API for IP tables. The API is represented by a set of set-to-cop system calls. Most important of them are soGetInfo, soGetEntries, and soSetReplace. soGetInfo is used by user space to get basic information about a table, its size, number of entries, and offsets into a blob for each of the used hooks. soGetEntries actually reads tables blob from the kernel, and the new blob is installed by soSetReplace set-to-cop call. So whenever a new rule is added or modified, the sequence of actions is to first get the current configuration via getInfo and getEntries, and try to apply a new one via soSetReplace. Interestingly enough, that this interface doesn't have any guards to prevent data races, and IP tables in user space implements its own locking. When a blob is loaded into the kernel, it is checked that it is valid, and the blob is updated to set up pointers to kernel data structures for matches and targets. After a new configuration is installed, it is ready for interpretation. The user space is responsible for parsing text representation of rules and creating the resulting configuration blob that is passed to the kernel via kernel API. The user space is composed of helper libraries, libiptc and libxtables, and binaries that use them, iptables, iptable-safe, and others. Hirim's law says that there are other third-party consumers of the kernel API. So now when we have a good understanding of how IP tables works, let's move our discussion to BP Filter. As I mentioned earlier, the idea of BP Filter was introduced back in 2018 by Daniel Borkman and David S. Miller. It got a lot of discussion and even its first knock. So what was the idea behind the patch set? The idea was to more or less transparently for an end user replace implementation of the IP tables. Let's review how BP Filter is organized and how it might be used to replace IP tables. BP Filter is implemented as a user mode helper. User mode helper allows to offload part of module's functionality to a user space process. A kernel modular with user space helper consists of a user space process and the communication channel between the kernel part of the helper and the user space process. The communication channel is implemented as a couple of pipes from kernel to user process and back. In a user process, these pipes are accessible through std in and std out. The communication channel allows passing arbitrary messages between kernel and user space parts. This way, it's possible to implement part of the functionality in a user space process. The kernel part of the module is responsible for setting up the communication channel, starting the user space process, and it's part of the logic. The similar approach is used for loading kernel modules. The kernel starts a helper user process that is responsible for handling all the machinery required to load the module, as it's not an easy task to do the same from the kernel. There is a simple serialization mechanism of the communication channel that allows passing messages on both sides. This allows the kernel to make a LPC call to the user mode driver and receive an answer back. Another interesting feature that's possible by using a user mode helper, there is a set of ready-to-use tools and instruments for user space code. For example, while working on BP Filter code, I'm using sanitizers and debugging tools to hopefully improve code quality. Using a well-established test infrastructure is another benefit given by this approach. Interestingly enough, that all codes of BP Filter might be tested purely in user space because it's possible to pass arbitrary file descriptors as std in and std out for the BPF filter process and thus have a shim layer. As we saw earlier, IP tables has multiple cornerstones: data structures, kernel API, and rules processing logic. How are those parts transparently replaced by BP Filter? If you want to keep IP tables ABI, it's not possible to change the used data structures. So the user space consumers of IP tables API continue to use the same data structures for rules. There is no change. It means that all the changes have to be done in the kernel space. For this purpose, the kernel part of the BP Filter is responsible for hooking into kernel IP tables ABI. The hooks are placed into the IP table sets of opt calls, handling routines, and simply pass the control to BP Filter kernel modular part. The BP Filter kernel modular starts a helper user space process if that doesn't exist and passes serialized messages over the communication channel to the BP Filter user space process. The serialized messages contain information about speed of the caller process and the arguments that were passed to the sets of opt call. The BP Filter user space process waits in the loop for new requests on the communication channel, handles them, and writes responses back. From a serialized message, BP Filter knows by whom what kind of operation is executed and what are the arguments. Then it uses process VM readv and to read the supply to sets of opt memory buffer from the caller process. And at this moment, BP Filter perfectly has all the required information to process the request. The similar approach is used to write the response back. As soon as the request is processed, an answer is written back to a supplied by caller memory buffer via process VM write-v, and the return code for the set-to-opt operation is passed back to the kernel part of the module. And finally, the kernel part of the module finishes execution of the set-to-opt call and returns control back to the user space caller. In this way, it's possible to transparently intercept set-to-opt calls and save the expected behavior. Let's briefly review these steps again. libIPTC, or third-party application, makes a set-to-opt call. Set-to-opt handling routines in the kernel ensure that BPF filter process exists and make an RPC request to user space BPF filter process. The request contains information about arguments, about origins of the set-to-opt call. The BP filter user space process reads the supplied memory buffer through process VM readv, handles it, and writes the answer back to the caller's memory buffer by process VM write-v. and returns an LPC response that contains the results for the sets-of-ops call. The kernel passes control back to the caller. Now let's review what the user space BPF filter process does in the middle of interception. We'll review the most important sets-of-ops call, so set replace, as this call is used to install a new version of the rule set. Conceptually, what BPF filter has to do, generate an equivalent version of the supplied rules in the form of one or more BPF programs and maps, load those programs and maps, and attach them. We will use table filter as an example because probably it is the most often used table and because it's already partially supported in BP filter. Table filter contains 3 hooks: input, forward, and output. Rules from these chains are applied to packets destined to the machine, forwarded through the machine, and for locally generated packets. For input hook, a BPF XDP program is used. For the output hook, it is possible to use a TCBPF program on the egress side. And while the forward hook isn't supported yet, probably it might be possible to use a TCBPF ingress program. I will focus on input and output hooks, but the same logic should be relevant for forward hook. The first step that BPF filter does, it parses a configuration block with a new set of rules. The same set of verification checks as IP tables does is performed by BP filter. It is supposed that a rule that doesn't pass a verification check by IP tables won't pass the same check in BP filter and vice versa. Any difference here isn't intentional. After the verification process is finished, the parsed configuration block is used to generate BPF programs and map that represents an equivalent form of rules. When programs and maps are ready, BP filter tries to load them and attach. If this step is successful, the pass block generated programs and maps are used to handle the remaining sets of opts, sockets info, socket entry, and others. Using XDP BPF program imposes some limitations and provides some benefits. The benefits is that if you have to filter a lot of traffic in the input chain, it might be very efficient, and we will talk about it later. And the limitation is that only one XDP BPF program might be attached to a particular network card at the moment. It means that if you have to use any other XDP program, there will be a conflict. This limitation might be solved by adding an indirection layer, a special BPF XDP chainer program that will call multiple programs. The issue is that there is no standard way to do it. Another drawback is that currently it's not possible to atomically replace BPF TC program, but hopefully it will be soon because there is work in progress. Besides that, it's not possible to atomically replace multiple BPF programs. Also, probably it is possible to overcome these limitations for common cases. To the current moment, we shall have a good understanding of what BPF filter is. Conceptually, this is a user space process that has a RPC-based API. During its lifetime, it generates BPF programs and maps, loads, and attaches them. Being a user space process gives another strong benefit: security. Relying on a common security barrier gives echelon defense. Even if there is a bug in parsing or checking a block or in code generation that results in a malicious BPF program, then there is another layer that should prevent such programs from loading, and we may expect misbehavior instead of a risk of arbitrary code execution. Let's discuss how BPF programs are generated. First of all, it seems that there are 2 conceptual ways how rules may be executed in a BPF program. The first way is to translate a rule into a set of instructions that will be applied to a packet. For a simple rule that, for example, matches against source and destination level 4 ports, this matching program will consist of BPF instructions that parse level 3 header and compare packets ports against specified values in the rule. In other words, in this approach, each rule has its own set of matching instructions. On the one hand, this is ideal from the performance point of view because there is no any indirection and the instruction directly comprise what has to be done to match a rule. On the other hand, there is a verifier's limit on complexity and size of a BPF program, so this approach won't work for large rule sets. The second way is to use one set of instructions to handle all the rules. In this approach, there will be a BPF program that is ready to handle any possible rule that it may encounter. Here we have the same set of instructions that is able to handle any possible rule. Because this approach uses indirection, it should be less performant than the first approach. At the same time, because there is one program to handle all possible rules, it could help us to process really large rule sets. There is a BPF helper, BPF for each map LM, that calls a supplied BPF function for each element of a map. It means that if there is a BPF map with some representation of rules and the BPF function, that it might be used to overcome the verifier's limit on complexity and size of BPF filter BPF programs. It seems that the combination of these approaches might be a middle ground. The first approach might be used for a small subset of a rule set that is most critical from the performance perspective, while the long tail of rule sets might be handled by the second approach. Iptables linearly tries to match a packet against rules until there is a match. This is why Iptables users try to optimize this process by placing rules that handle most of the packets closer to the beginning of a chain. This perfectly matches with the combination of two approaches. Hot rules use the first approaches, while cold rules use the second one. At the moment, version 2 of the patch set for BP Filter, BP Filter supports only the first approach for code generation. There is work in progress for the second approach. Let's briefly review how code generation works. I won't be digging into details because they are subject to change. Instead, I will try to give a bird's eye view on it. Here's an example of rules. The input chain for the filter table has a default policy accept and contains 3 rules that match by source, destination addresses, and level 4 ports. These rules are applied through iptables legacy restore, which is a binary that uses iptables set-sock-opt interface instead of using NFT. And after rules are restored, the network interface has an attached XDP program with ID 19. Let's review how code generation works for the first approach. The resulting BPF program is composed of a prologue, a set of instructions for rules, and an epilogue. The purpose of the prologue is to prepare an environment for executing rules instructions, because different program types have different context. The epilogue is responsible for the same goal, but at the end of the program, it cleans the environment. For example, different program types have different return values. Rules instructions are responsible for actual logic specified by rules. There is a calling convention that specifies what rules their matches and targets may expect and what they have to follow. In other words, this calling convention specifies a call interface. A set of instructions for a rule may be viewed as a set of comparisons. Each comparison is responsible for some parts of a rule. For a rule that compares by source and destination level 3 addresses, there are 2 comparisons: compare source and destination level 3 addresses. If comparison is false, the execution flow has to jump to the next rule. And if comparison is true, the execution flow has to proceed with the next comparison or target if there are no more comparisons left for the rule. Jumping to the next rule requires an offset that depends on the size of the generated instructions for the rule. Because the size of the generation of the generated rule isn't known until there is a until the rule is fully generated, the code generation supports fix-ups to support data that isn't known until even later phases. For example, until BPF maps are loaded and their file descriptors are known. The code generation supports relocations. Because multiple rules may access the same data from a packet, the code generation supports runtime context, which is a struct that contains frequently required data like pointers to level 3 or level 4 headers. Because instructions are emitted for each individual rule separately, and because the context is clearly known, it gives a lot of opportunities for optimizations. For example, let's take a look how UDP port matching is implemented for iptables. Here we perfectly see that there is no way to utilize some specific knowledge about a concrete rule. Instead, it has to assume a general case, and there is no way to optimize port matching for a single port instead of a port range. On the contrary, for BPF filter, because BPF filter perfectly knows the context, it may emit a single comparison with a constant for a case of a single port. I'm not saying that this is the most critical place from the performance point of view, but it clearly shows that more accurate and instructions are possible in case of BPF filter. As I said earlier, the work is in progress for the second approach of code generation that shall allow us to have pretty large rule sets while using BPF for each map LM helper. In this approach, code generation will generate a BPF function and one or more BPF maps. The maps will store an internal representation of the rules. It's not possible to reuse the existing IP tables blobs because BPF maps don't support variable-sized values. The function will be able to process elements in the maps and interpret rules. To support various types of BPF programs, code generation uses a common driver and dispatches to a polymorphic interface when specific for a program type instruction must be emitted. This way supports new program types easily, only the interface should be implemented. Let's briefly talk about performance. I don't think that BPF filter is in a state where exhaustive performance testing is an appropriate thing, but because it was mentioned in the version 2 of the patch set, I will repeat it here. On some simple and artificial filtering tests for input traffic, BPF filter showed advantages in performance. On a single core, BPF filter was able to filter out 900 of millions of small packets UDP traffic while still having 30% of the core free on commodity hardware. IP tables at the same time was able to filter out only 200 of millions. This was possible because the XDP hook is processed much earlier in the life of a packet, thus saving us a lot of CPU cycles. In the second test, available system resources are measured via StressNG tool, and the traffic with various firewall is the IP tables, NFT, or BPF filter. The main purpose of this performance testing was to show that there might be cases when the architecture of BPF filter might provide performance benefits in comparison to IP tables. Full description of the testing environment and methodology is available in the version 2 patch set. And now let's talk about limitations of BPF filter. Not all IP tables extensions might be implemented for BPF filter at the moment. For example, currently it's not possible to implement functionality of a LED target as there is no BPF helper for blinking lights. Hopefully, it should be possible to implement popular extensions with the help of existing BPF helpers or by adding new helpers. Another part of IP tables functionality doesn't have a direct analog. For example, support of namespaces by IP tables, and I'm not sure if it is possible to achieve it. In other words, 100% compatibility with IP tables isn't the right goal. Instead, focus should be shifted to the most often used and popular functionality. Also, there are concerns about the user space nature of BPF filter. Someone might kill a process or attach to BPF filter via ptrace. After all, these security concerns were the reason why BPF filter got its first NAC. If someone has enough privileges to modify a process owned by root, what would prevent them from modifying IP tables binaries and thus affecting how the system works? What I mean here is that every possible vector of attack should be reviewed and discussed independently. Hopefully, most of the suspicions come from BPF filter's original design. And future, a lot needs to be done. With the next version, code generation, hopefully there will be a skeleton for code generation and other parts will take shape. The first step will be to add new matches and targets to reach more compatibility with IP tables. Successor of IP tables, NFT, provides a tool to translate rules from IP tables format to NFTs format. This is the way IP tables tools work on a system where NFT is enabled. Having a tool that translates rule from NFTs format to IP tables should give a way to switch from NFT to BPF filter. Another option is to provide its own user space interface for BPF filter. BPF filter is a typical daemon, so nothing prevents it from having its own interface with command line utilities that give extended functionality. For example, this interface may allow injecting rules that are represented as BPF programs following some convention. This will allow an arbitrary flexibility that still has a solid security frame because there is a BPF verifier's guard. Another possible area of use for BPF filter is containers. There is a program type BPF proc cgroup SKB, which allows to attach BPF program to every input put SKB for a special C group, avoiding using early socket demuxing or IP tables. This may be achieved by using an extended interface for BPF filter in combination with or without systemd. Pondering about its user space nature of BPF filter allows us to imagine a case when BPF filter might be updated to a newer version purely in user space. This may be implemented by execute to a newer version of BPF filter while passing resources and state from the old binary to a new one. Privilege separation might be introduced for BPF filter user space process. A less privileged part might generate BPF programs and maps, while a more privileged part loads and attaches them. And it should be possible to add some simple optimization for the resulting program, something like a pip hole optimizer. The optimizer should find code patterns in the generated program and replace them by the optimized versions. And we have briefly reviewed how IP tables works, how BPF filter replaces parts of IP tables functionality. I hope that to this moment it's clear that BPF filter might be viewed as a compiler. It analyzes IP tables rules and synthesizes an equivalent BPF programs. Despite the fact that BPF filter tries to replace IP tables, 100% compatibility isn't the goal. Instead, the goal is to provide some reasonable level of compatibility and win something by utilizing unique properties of BPF for network functionality. A lot has to be done, but I'm looking to the future with optimism. Thank you for your time and attention. I'm ready to answer your questions.
I am a little bit confused about the deployment model that this is for, right? Because it was my impression that the the whole reason to do this, hooking into the kernel to get the IP tables rules and translate them through the user mode helper, was that it could be a transparent drop-in performance benefit for IP tables without user space having to do anything. But you're hooking into the HTTP hook, so the rules are being executed in a completely different place with completely different semantics. So if you just want to write an HTTP firewall, why not just do its own user space utility? Or are you planning to add other hooks later, further down the line, or what's the idea here?
I think that the right answer is that if an external observer doesn't see any difference in the behavior, then it doesn't have probably any meaning at which point of the network stack those rules are executed. So if there is no difference in observed behavior, it's not possible to understand where those rules are executed. And the idea is to probably execute XDP. And the idea is to generate an equivalent version XDP program that is an equivalent version of the rules applied to IP tables.
So that means you also do things like a FIP lookup to figure out if the packet is going into the host before you drop it, or that sort of thing.
Am I right that you mean a case when the packet, so because XDP hook is executed significantly earlier than input hook for IP tables, do you mean a case when it's not clear if a packet is destined for machine or is forwarded through machine, right?
Yeah.
Well, a good question. I think that probably it's might be solved by introducing new attachment points, or it may be just because we are not providing 100% compatibility. It may be something that you have to know if you're going to use BP filter, for example.
Right. And then another question was the performance figures you showed. This was with the XTP hook as well, right? So that
Yes.
shows that XTP is a lot faster than the networking stack, but it doesn't show the firewall rule execution because you are sort of like you're skipping a lot of the performance benefit you're seeing comes from not building HKBs and dropping the packets at the XTP layer. And it doesn't come from the execution speed of the rules so much, I would expect. So I was wondering if you've tried benchmarking it with something that's a bit closer, like for example, just using the TC ingress hook, I would expect would be because it's interesting to see how much faster is it to execute the BPF hook, like the rules themselves in BPF compared to evaluating them in the kernel in the IP tables filter. But that's sort of obscured by the fact that HTTP is so much faster, I think. So I'm wondering if you have tried benchmarking it in sort of HKB land.
Yes.
Was it actually
as I said,
through hardware XGP or XGP generic? Because one of your slides said XGP generic.
No. On so the tests were performed on hardware version, and the slide uses just a generic. To answer your question, I think that the first point is that for some cases it doesn't matter. The thing that matters is the number of resources that you have for your space applications after filtering traffic, right? And the second performance test there, where we measure amount of available resources via StressNG tool, it perfectly shows that for BPF filter is significantly, not significantly, okay. For a case of BPF filters, there are more resources available than for a case of IP tables or NFT. And I perfectly understand that what you are trying to say is that probably using and measuring performance for a TC ingress or egress hook will give us completely different results. Yes, it's probably, but as I said, it's not the right moment to do this testing. And hopefully with the next version, we will see some other numbers.
All right.
In chat, sorry, I was about to ask the question from the chat. Purna, if I pronounce the name correctly, sorry if not. Thank you, is asking. Thank you, Dmitry, for the talk. How does the performance compare to IP tables when a large number of remote addresses or remote address ranges are provided in a rule set?
Yeah, it actually depends on how those rules are constructed, because if you are using, for example, IP set feature for IP tables and all rules are stored inside this IP set, well, for BPF, we may have a direct analog of it, and we can use BPF maps to store their addresses. And if rules are specified, so if rules just contain lists of source addresses or destination addresses, whatever, this is a second scenario, right? And for the first case, we don't have yet an equivalent for IP set, but hopefully we will have it someday. And for the second case, when addresses are specified in each individual rule, I think that the difference in performance probably might be shown by the first test, because for input hook, the case of 32 rules, if you see, if you check the version 2 of the patch set, you will see there that those 32 rules are comprised of matching by source or destination IP addresses. So the results from that performance test approximately answers your questions.
Daniel, you had a question?
Yeah, I had a question. So one of the original thoughts on the RFC patch said that we had back then was like whether like long term, whether like the hooks from NetFilter could then be replaced with just a BPF invocation, and that way to have them super lightweight, and also maybe yeah, like in that sense, I was wondering, I mean, since there was the comment from Toki and now like the one statement regarding the C group SKB hook usage, whether you looked into the feasibility of replacing the existing NetFilter hooks, like, you know, like as an initial step, also with aided code generation from within the kernel, where BPF programs can then call out to some of the old functionality, like the legacy functionality from NetFilter IP tables, for example, and then like replace it step by step from that angle as well. Like for example, we already have like code generator, like in-kernel code generator for XDP, like to avoid red pollines, just to name one. I was wondering whether some like an approach like this could also be feasible for the NetFilter hooks, and then like to attack this problem from that point.
Daniel, may I ask, are you proposing some like hybrid BP filter? Like BP filter will convert some rules from IP tables and then leave the rest to IP tables, and like put itself into NetFilter hook, so it will be truly 100% compatible then, including the blinking light.
I mean, I hope that one is going to be removed at some point. But I mean, yeah, like a hybrid approach, so that you have some part of it as an in-kernel code generation, which would optimize the hook itself, and then you know, like the other part calling into some of the existing IP table helpers, but at some point in the future, maybe this could then be step-by-step replaced with the BP filter stuff from the code generation that you have.
With kfront calls from BPF, you could just call into NetFilter themselves as a fallback, right? And then generate some bytecode that does the match. And if that doesn't match, you call into NFT or
yeah, something like that. Yeah.
I think that would make sense as an approach, and then have the actual hook be the NetFilter hook instead of using XTP, for example.
Well, it's hard for me to. I think at the moment I'm focused on the more simple issues and problems when we just want to have some reasonable code generation for BP filter, but using it in the scenario that you suggested, yeah, it sounds interesting. I think that unfortunately I have to think about it before, and I don't have any idea right now.
What's your own use case for using this? Like, why are you doing this work?
Well, it's maybe consider it as a hobby, and because I like it, and because it helps me to understand how things work.
Yeah, cool. That's an excellent motivation. I was just wondering if you had some like application for it yourself, or if it's just because you think it's
yeah, I understand that part. So my ex-company is probably interested in this works, but this is too early, right? So probably to be used in production, but they're looking for replacement of IP tables because they are not satisfied with NFT performance. And probably BP filter will help them. So they have a very simple set of rules that have to filter a lot of input traffic. And probably BP filter here will help them.
I think we're already 4 minutes out of time. Let's do one last question if anyone has. All right. I guess this is it. So, and we're out of time. So thank you, Dmitry, for presenting. Excellent talk. And this concludes our presentations for today. And as the last part for today, I want again to thank you everyone for joining, and thank you the sponsors that made it happen. And of course, have thank you the speakers gift, the sponsors, the Linux Foundation, and the planning committee for make it happen. We will continue tomorrow at 7 a.m. Pacific time. And have a great rest of your day. Goodbye.